The heavens are no longer still. They seem to be preparing for something significant. On October 27, 2025, Moscow is bathed in an unnatural, vibrant green light. A fiery celestial body streaks across the sky, an event captured by countless cameras and witnessed by thousands. This is not an isolated occurrence. Reports of similar phenomena are flooding in from around the globe. Fireballs, swirling lights, and ethereal trails piercing the atmosphere. Unlike anything previously recorded, all of this unfolds as the interstellar traveler known as 3E Atlas embarks on its closest pass to the sun. While some attribute these events to mere chance, others, like Stefan Burns, perceive a deeper connection. He envisions a grand, almost unimaginable plan, perhaps a colonization endeavor aimed at Jupiter's icy moons. He dubs this concept Project Dawn, a theory with a low probability, yet its timing is undeniably precise. Could this be the final act the sky's rehearsing? Join us as we delve into these unfolding events, for what lies ahead may fundamentally alter our perception of the night sky. If these mysteries intrigue you as much as they do me, please consider liking this video and subscribing to receive real-time updates as they happen. Part 1. The day the sky became a global sensation. Imagine this scene. It is October 27th, 2025, shortly after midnight in Moscow. The city is quieting down, vehicles are powering off, and the last trains glide silently through the darkness. Suddenly, without any prior indication, the sky ruptures with an incandescent green. For a brief 3 seconds, dash cameras throughout the city record what appears to be a tear in the very fabric of the atmosphere. An intensely emerald streak illuminates the night, transforming darkness into day. The celestial object fragments as it descends, breaking into smaller, incandescent fragments that cascade towards the horizon. Onlookers halt their vehicles, fumbling for their phones. Within minutes, the footage is disseminated across the internet. This is no isolated incident. Let's rewind to June of 2025, when a colossal fireball detonated over Georgia and South Carolina in broad daylight, its brilliance casting distinct shadows even at midday. Fast forward to August, and mesmerizing spiraling lights danced across the eastern sky, threads of luminescence that defied any conventional explanation. The collection of videos grows, each more perplexing than the last, all posing the same fundamental question. What is occurring above us? Here's a crucial detail that seems to have eluded many online discussions. All of these phenomena coincide with the approach of an interstellar visitor named 3E Atlas, also identified as C2025N1, as it draws nearer to the sun. Discovered in July of 2025 by the Asteroid Terrestrial Impact Last Alert System, this object is far from an ordinary comet. It is traversing our solar system on a hyperbolic trajectory, indicating its origin lies far beyond our star system, originating from the vast expanse between the stars. Its perihelion, the point of closest proximity to the sun, is scheduled for October 29th, 2025, a mere 2 days after the Moscow incident. 2 days. So the central question we will explore throughout this investigation is this. Is this a mere coincidence, a direct consequence of an external event, or something entirely different? Are we witnessing a grand display of natural astronomical phenomena, or are we on the verge of experiencing the prelude to a narrative for which we currently lack the vocabulary? The established facts are as follows. 3E Atlas was detected by automated telescopes tasked with identifying near-Earth threats. Subsequent observations by the James Webb Space Telescope and the Very Large Telescope revealed an anomaly. Its coma, the luminous shell of gas and dust surrounding the nucleus, is predominantly composed of carbon dioxide. This is peculiar, as most comets originating from our solar system are rich in water. This object exhibits a different characteristic. Its spectroscopic signature deviates from what is expected from indigenous icy bodies. It possesses a chemically foreign composition, a traveler bearing the imprint of another stellar formation. Current ephemeris data, the predictive calculations of the object's future position and timing, indicate no risk of impact with Earth. Let us be However, proximity to potential danger and proximity to profound mystery are distinct concepts. Observe the public's reaction to these occurrences. In Moscow, following the fireball, church bells spontaneously chimed in several districts. News outlets struggled to keep pace with the deluge of eyewitness accounts. The societal impact of these events is what propels this narrative forward. Fear often escalates more rapidly than scientific caution because visual evidence is immediate. You witness a green fire in the sky, and your mind, without awaiting peer review, instantly crafts an explanation. Add to this the phenomenon of social proof. Millions of individuals sharing the same visual evidence, amplifying the same inquiries, and in the absence of an immediate, definitive explanation, the result is a rapid spread of conjecture. This presentation will examine 4 distinct avenues. Firstly, we will explore naturalistic explanations, such as meteor showers, atmospheric chemistry, and the remarkable yet ordinary events that transpire when celestial bodies interact with our atmosphere at immense velocities. Secondly, we will scrutinize the instruments and the data they collect, examining the tension between what sensors can detect and what human perception desires to interpret. Thirdly, we will investigate institutional responses, analyzing how governmental and scientific bodies communicate or fail to communicate during periods of cosmic uncertainty. Finally, we will engage in a speculative thought experiment, considering a maneuver known as an oath maneuver and a low probability hypothesis pertaining to Jupiter's moons. We will clearly denote speculative content when it is presented. The Moscow event serves as our focal point. Multiple dash cameras captured the incident from various vantage points, providing a rare opportunity for triangulation, a scenario astronomers dream of. The footage clearly depicts typical
32 seconds
fragmentation
into the flight.
behavior, an initial
The 3
intense
liquid fuel main
brightness,
engines soon
followed
will
by
throttle back to
progressive
72% of
disintegration,
rated
and
performance down in the
subsequent
bucket, reducing
secondary
the stress
flares
on the
as
shuttle as it
fragments
goes
break apart
transonic.
under aerodynamic stress. Eyewitness testimonies employed descriptive terms such as alien-like and green fireball, phrases that, while dramatic, offer valuable insights into color, temperature, and emission spectra. Social media activity surged within seconds of the event, generating a digital reverberation that circled the globe faster than the meteoroid itself descended. Herein lies our journalistic boundary. Verified footage requires multiple independent sources corroborating timestamps and validated metadata. Unverified footage remains in a state of uncertainty. Citizen camera compilations are pending professional triangulation, a process that essentially means we require further mathematical analysis before any definitive conclusions can be drawn. We will exercise caution in our assertions, but we will also be transparent about what remains unknown.
Lift off.
Why is 3I
Space Shuttle
Atlas
Atlantis
significant to
mission
this
to
confluence
build,
of events?
resupply,
Because
and to do
infrequent
research
occurrences
on the
attract
International
attention.
Space Station.
Attention, in turn, generates
Houston now
context.
controlling.
This
Atlantis
is the
begins
first
its penultimate
interstellar
journey to shore up
object of
the
its kind
International
to be
Space
observed
Station.
in such detail during its perihelion.
Atlantis now
And
in
it
the
is
proper
occurring
alignment
during
for
a
its
period of
8.5-minute
elevated
line to orbit,
meteor
4.5
activity.
million
The
pounds of
collective
hardware and
human
humans
psyche
taking aim on
struggles
the
with
International
coincidence.
Outpost.
It actively seeks patterns, meaning, and narratives that connect disparate
30
elements.
seconds into the
When
flight,
astronomical
Atlantis
anomalies
almost 2 miles in
intersect with
altitude, almost
societal
6 miles
anxieties,
downrange from the
the
Kennedy Space
resultant
Center, already
confluence can
traveling
be
500
unpredictable.
miles an
We
hour.
will follow the light, the data, and the unanswered
The
questions
3 liquid
to
fuel main
ascertain
engines now
who is
throttling back to
authoring this
72%
celestial
of rated
narrative,
performance,
and
going
we
into
will
the bucket,
commence by
reducing the stress on the
evaluating the
shuttle as it breaks through the
probabilities
sound
involved.
barrier.
Part 2, cluster analysis, timing, geography, and probability. Visualize a map of Earth and begin marking locations. Moscow on October 27th, Georgia and South Carolina in mid-June, and the East Coast spirals in August. Now incorporate the numerous other reports that have been cataloged by the American Meteor Society Network, the NASA Fireball database, and the European Space Agency's tracking systems. At first glance, the pattern appears alarming, suggesting an increasing frequency of objects impacting our atmosphere. However, it is crucial to provide context that is often lost amidst widespread panic. We are currently experiencing an overlap of several meteor showers. The Orionids reached their peak between October 21st and 22nd, a dependable annual stream of debris originating from Halley's Comet. Immediately following them, the torrids began to intensify. Active from late October through early November, the torrids are renowned for producing exceptionally bright fireballs, the kind that capture headlines and bring traffic to a standstill. Both of these showers were active during the same time frame that 3E Atlas was approaching. Let us consider the statistics. On an average night outside of any major shower activity, Earth encounters approximately 5 to 10 bright fireballs visible to the naked eye across the entire planet. During periods of strong shower overlap, this number can triple or quadruple. Furthermore, we now possess more cameras observing the sky than at any other point in human history. Dash cams are ubiquitous in Russian vehicles. Doorbell cameras are common in American suburbs, and smartphones are in virtually every pocket. The observed increase in detection is not indicative of a more active sky. Rather, it reflects our enhanced ability to perceive what has always been present. This phenomenon is known as detection bias, and it is fundamental to understanding why the sky appears to be experiencing such unusual activity. Imagine installing a dozen new smoke detectors in your home. Suddenly, you become aware of every piece of burnt toast, every candle flame, and every wisp of steam from your shower. Your house is not inherently more prone to fires. You are simply more attuned to the signs. The same principle applies to meteors. Camera density has surged dramatically over the past decade, and daylight-capable cameras are increasingly proficient at capturing bright events that previously went unrecorded. Social media amplifies awareness during periods of heightened sensory input, creating feedback loops where one sighting encourages others to observe and report their own experiences. Triangulation is the method by which we differentiate genuine patterns from apparent ones. When multiple observation stations record the same event from different angles, it becomes possible to reconstruct the meteoroid's trajectory, calculate its altitude, estimate its mass, and extrapolate its origin. The American Meteor Society operates a network of volunteer observers dedicated to precisely this task. NASA's Meteoroid Environment Office correlates satellite infrared detections with ground-based observations. These systems can determine whether a fireball aligns with a known meteor shower radiant, the point in the sky from which shower meteors appear to originate, or if it is a sporadic interloper with a unique orbit. The Moscow bolide exemplifies a textbook case. The recorded timeline indicates the event persisted for approximately 3 seconds, from its initial illumination to its ultimate fragmentation. The green coloration is consistent with the presence of nickel or magnesium in the meteoroid's composition, elements that emit characteristic wavelengths when superheated by atmospheric friction. The observed fragmentation pattern, characterized by progressive breakup and secondary flares, aligns with expectations for a stony meteoroid entering at high velocity and disintegrating under dynamic pressure. Preliminary triangulation, pending final verification from local observatories, and the American Meteor Society suggests an altitude profile consistent with atmospheric entry between 80 and 30 kilometers. The physics involved do not indicate any anomaly. They strongly suggest a meteor. However, let us address potential false positives, phenomena that appear unusual but are not meteors at all. Rocket stages regularly re-enter Earth's atmosphere, tumbling slowly and generating spectacular spiraling contrails as they burn up. Satellite flares, brief reflections of sunlight off flat orbital surfaces, can mimic moving lights. Ionospheric effects, disturbances in the upper atmosphere caused by solar activity, can produce luminous phenomena that exhibit movement and pulsing in seemingly impossible ways. The spiraling lights observed over the East Coast in August, for instance, bear a striking resemblance to the exhaust patterns documented during satellite deployments in previous years. While not identical, the similarities are significant enough to warrant comparison before hasty conclusions are drawn. Now let us conduct a probability-based thought experiment. Assume on average we anticipate 10 high-visibility fireballs per week during a period of low activity. During the peak of overlapping meteor showers, this number might increase to 30 per week. If we consider a 6-week window from mid-September to late October, We would predict somewhere between 120 and 180 bright events globally. The apparent surge in reports may simply reflect this predicted increase, amplified by detection bias. Conversely, if the actual count significantly surpasses this range, it would provide grounds for deeper inquiry. The challenge lies in the absence of comprehensive global data. We possess fragmented reports, variable detection thresholds, and a media landscape that prioritizes the dramatic over the mundane. This is where institutional capacity becomes paramount. We require more professional triangulation. We need sensor correlation that transcends national borders and integrates diverse data types: optical, infrared, infrasound, and radar. We need the painstaking, unglamorous work of verification, which takes weeks rather than seconds. The American Meteor Society and NASA are undertaking this critical work, but they are engaged in a race against the speed of social media, a competition that no one truly wins. The primary accelerant in this cultural phenomenon is 3 Atlas itself. This interstellar object, chemically unusual and rapidly approaching its closest point to the sun, serves as the narrative anchor for every unexplained light in the sky. The precise connection between the comet and the observed meteor activity is secondary to the public's belief that such a connection might exist, and belief is an extraordinarily powerful driving force. So, what precisely is this celestial visitor? And why has it captured the attention of everyone from amateur astronomers to doomsday prophets? Part 3. Caught in the middle. Why 3i Atlas matters. Let us establish with absolute clarity what 3i Atlas is and is not. It is not a meteor shower. It is not debris from a defunct satellite. It is an interstellar object officially designated 2025 N1, a visitor from beyond the confines of our solar system. The term interstellar object precisely describes its nature. This entity originated elsewhere, around a different star, within a molecular cloud entirely unconnected to our sun. It has journeyed through the galaxy for an indeterminate period, and is now passing through our celestial neighborhood on a trajectory that will ultimately lead it back into the void. The Atlas Survey, a network of robotic telescopes designed to detect asteroids posing a threat to Earth, identified it in July of 2025. Initially, the discovery was routine, merely another faint smudge moving against the backdrop of stars. However, subsequent observations unveiled something extraordinary. The object was traveling on a hyperbolic orbit, indicating it possessed sufficient velocity to completely escape the sun's gravitational influence. This is the definitive signature of interstellar origin. Objects born within our solar system are gravitationally bound. They orbit and eventually return. Interstellar visitors conversely pass through once and do not reappear. Following this, spectroscopic analysis was performed. Both the James Webb Space Telescope and the Very Large Telescope in Chile directed their instruments toward 3i Atlas, dispersing its light into component wavelengths to ascertain its composition. The findings revealed a coma dominated by carbon dioxide rather than water vapor, which constitutes the primary component of most comets. Carbon dioxide implies a divergent
32 seconds into the
history,
flight.
a different thermal
The 3 liquid
environment,
fuel main
and
engines
possibly
soon
a
will throttle
different
back to
region within a
72% of
distinct
rated
stellar
performance
system
down in the
where
bucket,
ice
reducing
formed
the
under
stress on the shuttle as it goes
conditions dissimilar
transonic.
to those of our primordial disk. It is akin to encountering an individual who speaks a language that is vaguely familiar yet ultimately indecipherable as the comet approaches its perihelion, scheduled for October 29, 2025. It is subjected to intense solar radiation. This heating process drives sublimation, the transformation of frozen volatiles directly from a solid to a gaseous state without passing through a liquid phase. For an object rich in carbon dioxide, sublimation occurs at different temperatures compared to water ice, which consequently alters the behavior of its jets and outgassing. Consider it akin to different fuels burning at varying rates. The comet is expelling gases, and the sun is intensifying this process. Sunward jets are of particular interest as the nucleus rotates, exposing different areas to the sun. Gas erupts in plumes
Liftoff
subtly
of Space
alter
Shuttle
the comet's
Atlantis.
predicted
Mission
trajectory.
to build,
These
resupply,
non-gravitational
and to do
accelerations, while
research on the
minute, are
International
measurable.
Space
They
Station.
complicate orbital predictions
Houston now
because the
controlling.
system is
Atlantis
no
begins
longer
its
governed
penultimate
solely
journey
by
to shore up the
gravity.
International
It is
Space
influenced
Station.
by a form of propulsion, albeit
Atlantis now in
uncontrolled
the
and
proper
driven
alignment for
by
its
solar
8.5-minute
heating
ride to
rather
orbit,
than
4.5
intentional
million
thrust.
pounds of
This
hardware and
observation
humans
becomes
taking aim on the
relevant later
international outpost.
when we discuss whether any observed trajectory deviations might be deliberate rather
30
than
seconds into
natural.
the flight,
The
Atlantis
operational
almost 2
challenge
miles
is
in altitude,
considerable.
almost 6
Observing a
miles
comet in
downrange from the
close
Kennedy Space
proximity
Center
to its
already, traveling 500
perihelion is
miles an hour.
exceptionally difficult. The object is situated near the sun and
The
the
three
sky,
liquid fuel main
leading to
engines now
glare
throttling
that
back to
necessitates
72% of rated
extreme
performance,
caution
going
for
into the
instruments
bucket, reducing
to
the
avoid
stress on the
damage.
shuttle as it breaks through the sound
Coronagraph
barrier.
telescopes designed to obscure the sun's disk, enabling the observation of the corona and nearby objects, are the primary tools during this period. However, they are prone to saturation, produce artifacts, and create gaps in coverage. To the public, these observational gaps can appear suspicious, suggesting concealment. To astronomers, they represent the frustrating reality of attempting to photograph a faint, rapidly moving object adjacent to the brightest entity in the solar system. The cultural dimension is where the situation becomes volatile. Scientific rarity is inherently captivating. When combined with mystery, the unanswered questions regarding composition and origin, and accessible imagery, those stunning false color images from space telescopes, the result is a potent recipe for virality. 3 Atlas is not merely scientifically intriguing, it is culturally magnetic. Every tweet, every article, and every breathless YouTube video contributes to a reinforcing feedback loop. The object transforms into a screen onto which individuals project their hopes, fears, and wildest imaginings. Now let us address the doomsayers. The ephemeris data, the mathematical model of the comet's trajectory, is publicly accessible and verifiable through NASA's Horizon system. Its closest approach to Earth never approaches collision proximity. We are discussing clearance of millions of kilometers. This is not a scenario akin to Chicxulub or deep impact. The comet will arc around the sun, gain a gravitational slingshot boost, and then resume its course back into interstellar space, likely never to be seen again within the lifespan of human civilization. The threat is zero. The intrigue is infinite. However, this presents a double-edged sword. Because 3 Atlas is scientifically compelling, it has become culturally combustible. The legitimate questions posed by scientists, queries regarding composition, origin, and orbital mechanics, become intermingled with illegitimate questions. These include inquiries about alien probes, government cover-ups, and apocalyptic prophecies. This admixture is volatile and fuels every subsequent ambiguity. When data gaps emerge, when instruments go offline, or when official statements are delayed, the culturally combustible nature of this event transforms uncertainty into alarm. Therefore, our current situation is this: a chemically unusual interstellar visitor is nearing its closest approach to the sun, precisely as Earth is experiencing a statistically plausible, yet visually dramatic increase in meteor sightings. The timing is sufficiently noteworthy to attract attention, but not anomalous enough to definitively prove anything. Into this void between suspicion and proof, a torrent of information, misinformation, and speculation is pouring. The next crucial question is, why are official channels so slow to respond? And what transpires in the silence they leave behind? Part 4. Information, friction, data gaps, delays, and the amplification of the narrative. Let us map the timeline of public perception versus institutional releases. On October 27th, the Moscow fireball becomes an internet sensation within hours. By October 28th, speculation is rampant across social media platforms. Meanwhile, the initial official statement from Russian astronomical authorities is not issued until October 30th, a delay of 3 full days. The National Aeronautics and Space Administration's Meteoroid Environment Office provided an initial announcement on November 1st. Subsequently, on November 3rd, the European Space Agency issued an update regarding 3 observations of Comet 3I Atlas near its closest approach to the Sun. Observe this sequence. The intervals between these occurrences and the official clarifications are substantial. creating fertile ground for speculative theories, which indeed flourish. This phenomenon is not necessarily a result of deliberate deception or oversight. Rather, it reflects the operational dynamics of scientific endeavors at an institutional level. Images captured by chronographs necessitate processing to eliminate extraneous noise and anomalies. Likewise, preliminary orbital calculations require verification against multiple sets of observations to guarantee their precision. The calibration process itself is time-consuming, as scientific instruments are highly precise tools, not consumer-grade devices. The scientific methodology incorporates
32
numerous
seconds into
layers
the
of
flight.
validation, specifically
3 liquid
to
fuel
prevent
main
the
engines soon will
dissemination
throttle
of
back to
inaccurate
72% of rated
data.
performance down
However,
in the
these
bucket,
crucial
reducing the
steps
stress on the
require
shuttle as it goes
time, a
transonic.
commodity that the internet often lacks patience for. Science operates with a review board, while social media offers a single action: post. Consider a concrete illustration: the assertion of missing image frames around the comet's perihelion. Numerous astronomy forums and video channels highlighted apparent breaks in the imagery from Soho's LASCO coronagraph during the critical hours when Comet 3I Atlas was nearest the Sun. The unspoken implication, amplified across numerous comment sections, was that certain frames had been intentionally removed or withheld to conceal information. The actual explanation is far more conventional. Coronagraphs employ protective operational modes when directed towards intensely bright celestial objects.
10, 9,
Automatic adjustments
8,
to exposure
7,
settings can
6,
inadvertently
5,
introduce temporal gaps.
3,
Camera saturation occurring when the sensors are
0,
overlaid by light.
and liftoff of
Corrupted
Space Shuttle
frames which are
Atlantis on
subsequently
a mission
omitted
to build,
during the data
resupply,
processing phase.
and to do research
Solar
on
glare,
the International
deactivation
Space
of
Station.
protective instrument protocols,
Houston now
delays of
controlling.
data
Atlantis
transmission
begins its
collectively
penultimate journey to
contribute
shore
to
up the
what
International
might appear
Space
as
Station.
censorship, but is in reality a consequence
Atlantis
of
now in the proper
engineering
alignment for its
constraints.
8.5-minute
Furthermore,
ride
the
to
phrasing
orbit,
of
4.5
official
million
statements
pounds of hardware
can
and
be
humans taking aim on the international
ambiguous.
outpost.
When an agency states that no unusual activity was detected, does
30
this
seconds
imply
into
that
the
a
flight,
thorough investigation
Atlantis
yielded
almost
no
2 miles in
findings, or simply
altitude,
that
almost
the
6 miles downrange from the
investigation
Kennedy
had not
Space
yet
Center already,
commenced?
traveling 500
When a
miles an
press
hour.
release indicates that data analysis is ongoing, is
The
this
3
a
liquid fuel
coded
main
message
engines
for
now
an
throttling
unknown
back to
outcome, or
72%
merely
of
a
rated
reflection
performance,
of the
going into the
standard
bucket,
research
reducing the stress on
timeline?
the shuttle as it breaks
The
through the
range of
sound barrier.
interpretation is vast, and any ambiguity is readily exploited. Mainstream media outlets, striving to balance accuracy with audience engagement, often resort to hedging their language, which can make them sound evasive even when exercising appropriate caution. It is here that we must introduce a dose of reality from those who directly operate these instruments. Imagine a senior mission scientist remarking, "We do not conceal any footage. Occasionally, we're unable to safely direct the instrument. At other times, the collected data is corrupted. In some instances, processing the recorded information takes several weeks." None of this constitutes a conspiracy. It simply represents the inherent limitations of conducting solar observation with sensitive apparatus. This statement, while factually accurate and entirely unremarkable, is conspicuously absent from discussions surrounding the dissemination of information. The mechanism by which rumors propagate is straightforward and relentless. A user isolates a brief segment of ambiguous visual material. An influential figure with a substantial following then republishes it, accompanied by an exaggerated caption. The platform's algorithm promotes it further due to a surge in engagement metrics. News outlets associated with these platforms, observing the increased traffic, contribute to the narrative. Within a 48-hour period, a minor observation transforms into a widely discussed topic, irrespective of its actual verification. This amplification loop is self-perpetuating and does not necessitate intentional malice, merely the pursuit of attention. Attention in the contemporary information landscape is the primary currency. This creates an ethical quandary for scientific agencies. They must navigate the imperative of transparency, providing public access to data and findings, against the risk of inciting alarm by releasing preliminary information that may later be revised. Planetary defense policies prioritize caution. Announcing a potential threat prematurely and being incorrect erodes credibility. Delaying too long and being correct could lead to loss of life. This trade-off is profoundly challenging, and there is no universally correct approach. Maintaining public tranquility and upholding scientific integrity are both vital objectives, but they do not always align seamlessly. For those seeking to navigate this complex information environment, consider this practical guidance on data provenance. When encountering an astronomical claim, inquire about corroboration. Have multiple independent observers reported the same phenomenon? Request spectral analysis. Does the observed spectrum correspond to a known elemental composition? Ask for instrument logs. Is there a time-stamped record of the observation complete with intact metadata? Warning signs include reliance on a single source of visual data, a lack of supporting evidence, claims that circumvent the peer review process, and assertions that a singular anomaly validates a grand conspiracy. Extraordinary claims demand extraordinary proof, and pixelated video clips from online platforms fall far short of this standard. When the pace of scientific inquiry is slow, sensational narratives rush to fill the void. This is the fundamental dynamic currently unfolding. The institutions are performing their designated functions, but their operational timelines are out of sync with the prevailing cultural rhythm. Within this temporal disconnect, something else emerges, something that warrants further discussion. How did a comet become the nexus for eschatological prophecies, conspiracy networks, and the resurgence of the biblical concept of wormwood? Why does apprehension spread more rapidly than factual information? And what are the implications when millions of individuals believe that the heavens are communicating directly with them? Part 5, exploring the cultural and contagious aspects from dashcam footage to doomsday scenarios. Pay attention to the trending topics. On October 27th, within 6 hours of the Moscow meteor event, the term dag wormwood began trending globally. By October 29th, the day of the comet's perihelion, Comet 3I Atlas was ubiquitous, interwoven with conspiracy theories, religious prophecies, and doomsday countdowns. Clergy broadcast live sermons interpreting these celestial events as harbingers of the end times. Podcast hosts meticulously analyzed frame-by-frame footage, searching for hidden patterns. Sentiment analysis of social media indicated a significant spike in fear in specific regions, particularly those with strong apocalyptic religious traditions, while sentiments of awe and curiosity predominated elsewhere. The same event, the same celestial object, was interpreted through vastly different cultural frameworks. Content that resonates emotionally is disseminated most effectively. Cognitive science has recognized this principle for decades. Fear and wonder are both high arousal emotions that stimulate sharing behavior. When you encounter something that causes your heart to pound, you feel an impulse to share it with others. This is the essence of the meme engine. The veracity or falsity of the content is secondary to its perceived importance. A green meteor fireball over Moscow feels significant. An interstellar comet with a peculiar chemical composition feels significant. The confluence of these elements feels apocalyptic, and apocalyptic narratives have consistently proven to be highly engaging. Let us now consider wormwood. Revelation chapter 8, verses 10 through 11, describes a star descending from the heavens, blazing like a torch, and poisoning a third of the rivers and springs. The name of this star is wormwood. For centuries, this passage has been interpreted as a prophecy of cosmic catastrophe, a celestial body bringing destruction to earth. Each time a bright comet or meteor appears, the verse is invoked, prompting speculation about whether this is the prophesied event. Halley's Comet in 1910 generated panic related to wormwood. The Tunguska event in 1908 was retrospectively linked to it. Now, in 2025, Comet 3I Atlas has become the latest candidate, and the symbolism is too compelling for believers to disregard. An object originating from space, appearing during a period of global unease, captured in numerous videos depicting unusual lights in the sky. This is not a theological assertion, but rather a cultural analysis. Eschatological narratives endure because they provide a framework for understanding chaos and imbue randomness with meaning. When the world feels precarious, the notion that events are unfolding according to a divine plan can offer profound solace, even if that plan entails suffering. The physical processes governing meteors and comets are indifferent to human narratives. However, human narratives are deeply influenced by physics when it manifests as celestial phenomena. Conspiracy networks seize upon various interpretations. Project Bluebeam, a long-standing conspiracy theory, alleging that global elites intend to employ holographic technology to stage a fake alien invasion or a religious event, resurfaces frequently during unusual celestial occurrences. This theory posits that by orchestrating a grand simulated spectacle, authorities aim to manipulate populations into accepting authoritarian governance. There is no credible evidence to support this scenario, yet its emotional resonance is powerful. If the sky can be faked, then anything can be faked. The Moscow meteor event is assimilated into this narrative framework. The aerial spirals observed in August are presented as evidence. Every perceived gap in the data is interpreted as proof of a cover-up. Alleged leaked footage, which either fails to materialize or is later identified as archival material from unrelated incidents, circulates widely because it aligns with the prevailing story. Let us examine a specific example. On October 30th, a YouTube channel boasting 2 million subscribers uploaded a video titled "NASA Hides Perihelion Footage. What Are They Afraid Of?" The video intersperses screenshots, speculative commentary, and out-of-context statements from scientists. Within 24 hours, it garnered 5 million views. The platform's recommendation algorithm suggests it to users who have previously engaged with space-related content. Mainstream media outlets then report on the controversy as a news angle. This surge in traffic generates substantial advertising revenue, reinforcing the cycle. The pursuit of truth becomes secondary to the drive for engagement. Cognitive dissonance and confirmation bias explain why adherents integrate new events into their existing belief systems rather than revising their perspectives. If one already harbors the conviction that the government conceals information, every official delay in statement serves to reinforce that belief. Similarly, if one believes that we are living in the final days, every unusual phenomenon becomes another sign. The human brain is predisposed to resolve cognitive inconsistencies by selectively embracing evidence that supports prior conclusions. This is an inherent characteristic, not a flaw. Consequently, debunking efforts are rarely effective. One cannot logically dissuade someone from a position they did not arrive at through logical reasoning. The attention economy exacerbates this dynamic. Content creators and influencers are not necessarily acting with malicious intent. They are responding to economic incentives. Views translate
32
directly
seconds
into
into the
revenue.
flight.
Controversy
The 3
generates
liquid
views,
fuel
and
main
therefore
engines soon will throttle back to
controversy
72% of rated
revenue.
performance
A
down in the bucket,
dispassionate
reducing the
explanation
stress
of
on the
meteor
shuttle as
shower
it goes
statistics
transonic.
does not attract significant viewership. A dramatic breakdown of alleged government censorship, however, does. The structural incentives inherently favor sensationalism, regardless of the creator's intent. Now let us consider the ethical ramifications. When widespread belief transforms into collective panic, tangible harm invariably follows. The Heaven's Gate cult in 1997 engaged in mass suicide based on the conviction that a spaceship accompanying Comet Hale-Bopp would transport them to a higher plane of existence, resulting in the deaths of 39 individuals. This occurred during an era of slower information dissemination. Today, with instantaneous global communication, the potential scale of panic-driven behavior is exponentially greater.
8,
We have
7,
not yet witnessed the
6,
most severe
5,
manifestation of violent
3,
but the
2,
infrastructure for it is firmly in place.
0.
The fundamental difference
Liftoff
between then
of
and
Space
now
Shuttle
lies in speed and
Atlantis
scale.
on a mission to build,
In
resupply,
1997, it
and
took
to do
weeks for
research on
French
the
belief to
International
achieve
Space Station.
widespread acceptance. In
Houston now
2025,
controlling.
this
Atlantis
process
begins its
takes mere
penultimate journey to
hours.
shore up the
The
International Space
interconnectedness
Station.
of networks is denser, algorithms
Atlantis
are
now
more
in the proper alignment
sophisticated,
for its
and the
8.5 minute line
barriers
to
to
orbit, 4.5
participation have
million pounds
vanished.
of hardware and
Anyone
humans
possessing a
taking aim on the
smartphone can
International
broadcast
Outpost.
their interpretation of celestial events to millions. This democratization
30
of
seconds
voice,
into the
while
flight.
empowering, also carries
Atlantis almost 2
significant
miles in
risks.
altitude.
We now
almost 6
arrive
miles
at the
downrange from
conclusion of the
Kennedy Space
initial
Center already,
phase, having
traveling
traced the
500 miles an
trajectory
hour.
of celestial phenomena, the flow of data, and the
three liquid
feedback
fuel main
loops
engines
within
now
social
throttling back to
networks.
72%
We have
of rated
established that the
performance, going into
scientific
the
tools
bucket,
employed
reducing
for
the stress on the
explanation
shuttle
are
as it breaks through
essential,
the sound
but
barrier.
insufficient. Institutional transparency is crucial, but so too are the structural forces that shape how information circulates within society. The sky is indeed conveying messages, but it is humanity that interprets their meaning. Currently, a multitude of interpretations are being put forth simultaneously. Some are rooted in physics, others in prophecy, and some are merely noise amplified by algorithms that cannot discern the difference. In the subsequent section, we will delve into the underlying mechanisms. Why do meteors emit a green glow? What phenomena occur when a comet approaches too closely to the sun? And what would it genuinely require for an extraterrestrial object to be more than just a celestial body composed of rock and ice? Let us investigate. Part 6. Physical mechanisms, the luminescence of meteors, and the spectacle of fireballs. Let us examine the reasons behind the colors displayed by celestial objects. Color in this context conveys information. When a meteoroid collides with Earth's atmosphere at velocities ranging from 11 to 72 kilometers per second, it does not combust in the conventional sense. Instead, it undergoes ablation, a process wherein its surface material vaporizes due to intense friction with atmospheric molecules. This resulting vapor cloud becomes superheated to thousands of degrees, reaching temperatures sufficient to excite atoms, causing them to emit light at specific wavelengths. These wavelengths are indicative of elemental composition. Nickel, for instance, produces a green spectral line at 520 nanometers. Magnesium emits a blue-green hue around 580 nanometers. Iron radiates a yellow-orange light at approximately 570 nanometers. Sodium, a common constituent of many meteoroids, generates a vivid yellow line at 589 nanometers. The observed color provides insight into the object's material makeup, at least partially. A predominantly green fireball suggests the presence of nickel or magnesium. Both elements are frequently found in certain types of stony meteorites and iron meteorites. There is nothing inherently unusual about green meteors. The intensity and duration of the green luminescence are contingent upon the quantity of nickel or magnesium present, and the rate at which the material ablates. A rapidly moving object with a high metal content will produce a brighter, greener glow compared to a slower, rocky counterpart. Fragmentation represents another significant spectacle. Meteoroids are not monolithic spheres. They are typically aggregates, often loosely bound collections of rock and metal formed in the low-gravity environment of the early solar system. As dynamic pressure increases during atmospheric entry, the object's tensile strength, its resistance to being torn apart, determines whether it remains intact or disintegrates. Dynamic pressure is a function of velocity squared and atmospheric density. At high altitudes where the atmosphere is thin, the pressure is low. As the meteoroid descends and the air becomes denser, the pressure escalates dramatically. If the tensile strength is exceeded, the object fractures. Each fragment then undergoes its own ablation process, generating secondary flares. The footage from Moscow illustrates precisely this pattern, an initial intense luminescence as the primary mass heats up, followed by progressive fragmentation with multiple smaller flares trailing behind. The terminal burst, the final and most brilliant flash, occurs when the largest remaining fragment disintegrates entirely. This is characteristic behavior for a bolide, so predictable that meteor scientists would be surprised by any deviation. Compare this event to other well-documented bolides. The Chelyabinsk meteor over Russia in 2013 exhibited a similar cascade of fragmentation, albeit on a considerably larger scale and at a lower altitude, resulting in a shock wave that caused structural damage. The fireball observed over the Midwestern United States in April 2023, captured by numerous weather radars and dash cameras, displayed the same green coloration and breakup sequence. These patterns are repeatable and well understood. Satellite infrared confirmations provide an additional layer of verification. When a large meteoroid explodes in the atmosphere, it releases a substantial amount of energy. Satellites equipped with infrared sensors designed to detect nuclear detonations also register bright meteors. Both the Department of Defense and NASA operate systems that log these events, recording the time, location, and estimated energy release. Infrasound sensors, which detect low-frequency sound waves capable of traveling long distances, can be used to triangulate the altitude and yield of atmospheric explosions. For the fireball observed over Georgia and South Carolina in June, both infrared and infrasound data corroborated the event, providing mass and energy estimates consistent with a meteoroid in the 1 to 10 ton range. Daylight fireballs are less frequently witnessed, but their occurrence is not less frequent. Most meteors transit Earth's atmosphere when human observation is not actively occurring. The probability of a bright fireball appearing during daylight over a populated area, with cameras operational and fortuitously capturing the event, is low for any single occurrence. However, over the course of a year, across the globe, several such events are anticipated. Detection thresholds are important. A meteor that would be strikingly visible at night might be barely noticeable in daylight unless it possesses exceptional brightness. The June event was luminous enough to cast shadows at midday, placing it among the most significant fireballs of the year, yet still within the expected range of occurrences. Now let us discuss the capabilities and limitations of citizen-contributed video. Parallax errors arise when attempting to ascertain distance or altitude from a singular camera perspective. A meteor that appears to be descending directly towards one's location might actually be 100 kilometers distant and 50 kilometers high. Focal length distortion, which affects how camera lenses magnify or reduce apparent size and distance, further complicates interpretation. A meteor appearing immense through a wide-angle lens could be small and far away. This underscores the critical importance of triangulation from multiple observation points. A single camera provides an aesthetically pleasing video. 3 cameras provide scientific data. The color of a meteor, its fragmentation pattern, its duration, and its infrasound signature collectively help to narrow down the classification of the object. Its color alone does not provide components. Orbital data is required, which necessitates precise measurements of trajectory and velocity from multiple angles. This is the work that takes weeks, not hours, and it is often overlooked when individuals are eager for immediate answers. We have now established that the physics governing fireballs is well understood and that the Moscow event aligns convincingly with natural explanations. But what of the comet itself? What transpires when an interstellar visitor ventures too close to the sun? Could such an interaction generate unusual phenomena? Let us explore this further. Part 7. Solar Comet Interaction. Jets, tails, and solar weather. Perihelion marks a transformative phase for a comet. At significant distances from the sun, a comet remains dormant, frozen, and inactive. As it approaches, solar radiation heats the nucleus, causing volatile compounds to sublimate. Water ice begins to sublimate at approximately 150 degrees Celsius. Carbon dioxide sublimes at much lower temperatures, around minus 78 degrees Celsius at 1 atmosphere pressure, and even lower in the vacuum of space. This indicates that a comet rich in carbon dioxide, such as 3I Atlas, will begin to release gases earlier and more vigorously than one primarily composed of water ice. Jets are formed when sublimation occurs unevenly across the surface of the nucleus. Imagine the nucleus rotating, exposing different regions to sunlight. The sunlit side heats up and releases gas. The shaded side cools and refreezes. If the surface contains patches with a higher concentration of volatiles or fissures that channel gas flow, directed jets will emerge rather than uniform outgassing. These jets can be powerful enough to generate measurable thrust, subtly altering the comet's trajectory. This phenomenon, known as non-gravitational acceleration, has been observed in dozens of comets over the past decades. In the case of 3I Atlas, with its notable abundance of carbon dioxide, The sublimation profile
32
deviates from
seconds
that
into the
observed
flight.
in typical solar system
The 3
comets.
liquid fuel main engines soon
Carbon
will throttle back to
dioxide possesses a
72% of
lower
rated
heat
performance down in
capacity
the
than
bucket,
water,
reducing the
meaning it
stress on the
responds
shuttle as
more
it goes
rapidly to
transonic.
temperature fluctuations. This could result in more erratic jet behavior, increased asymmetry, and greater unpredictability. The James Webb Space Telescope's spectroscopic analysis, which revealed the carbon dioxide-rich coma, is crucial here as it indicates we are dealing with a distinct entity. The fuel source differs, thus influencing the combustion process. The solar wind, a continuous stream of charged particles, electrons, and protons emanating from the sun, travels outward through the solar system at speeds between 300 and 800 kilometers per second. When this plasma encounters a comet's coma, it interacts with the ionized gases, creating a visible ion tail that invariably points away from the sun.
T-minus 10.
The dust
9,
tail, composed of
8,
larger particles
7,
propelled by
6,
solar radiation
5,
pressure, follows a different
3,
during periods of heightened solar activity,
0,
coronal mass ejection.
Liftoff
Massive
of
expulsion
Space
of
Shuttle
plasma and
Atlantis.
magnetic fields from
Mission
the
to
sun's
build,
corona
resupply,
can impact
and
the
to do
comet,
research
leading to
on the
disconnection
International
events where
Space
the
Station.
ion tail effectively
Houston now
detaches.
controlling.
and a
Atlantis
new one
begins its
begins to
penultimate
form.
journey to shore up the
These
International
unfolding
Space
events
Station.
are quite striking and have been thoroughly
Atlantis
documented
now on the proper
within the
alignment
field
for
of
its 8.5
cometary
minute line to
science.
orbit. 4.5
Instruments
million
such as
pounds
the
of
Solar
hardware and
Orbiter
humans
and the
taking aim
Solar
on the
Dynamics
International Outpost.
Observatory have diligently monitored solar activity throughout the entirety of the
30
year
seconds into the flight.
2025,
Atlantis
confirming
almost
that
2
our
miles in
sun is
altitude,
currently
almost 6
experiencing
miles
a peak
downrange from the
in its
Kennedy Space Center
approximately
already, traveling
11-year
500
solar
miles an
cycle.
hour.
During the month of October, several significant
The
coronal
3 liquid
mass
fuel main
ejections
engines
were
now
observed.
throttling back to
Some of these
72% of
eruptions
rated
were
performance
directed
going
away
into the
from Earth,
bucket,
while
reducing the
others
stress
passed
on
in
the
close
shuttle as it breaks through
proximity
the
to the
sound
orbital
barrier.
path of 3I Atlas. During its closest approach to the Sun, its perihelion. When a coronal mass ejection interacts with a comet, it can induce the formation of swirling patterns within the comet's tail, generate visual distortions due to magnetic field interactions, and cause temporary increases in brightness as the heightened flux of charged particles energizes more of the comet's coma. For individuals lacking a background in cometary physics, these observable phenomena might appear irregular or unexpected. For a solar physicist, however, this is where conjecture comes into play, clearly indicated as such. It's conceivable that heightened solar activity could stimulate an increased release of dust from 3I Atlas during its perihelion passage, potentially creating temporary meteoroid streams that could intersect Earth's orbital path. The underlying principle would operate as follows. Intense solar heating could trigger explosive outgassing from the comet, ejecting dust particles at velocities greater than typical. If the orbital geometry were such that Earth later traversed this newly formed dust trail weeks or even months after its creation, an observable increase in meteor activity would likely result. The probability of such an event occurring is considered low, as the dust would need to possess very specific orbital characteristics to intersect our planet's path. Furthermore, the ejection velocities resulting from cometary outgassing are generally on the order of a few hundred meters per second, insufficient to drastically alter dust particle orbits within short time frames. Nevertheless, the scenario is not physically impossible, merely improbable. Historical precedents do exist. For instance, Comet Bella experienced fragmentation during its perihelion passage in 1846, and the resulting debris eventually gave rise to the Andromedid meteor shower. Comet Shoemaker Levy 9, prior to its collision with Jupiter in 1994, broke into numerous fragments. Comet Linear likewise disintegrated during its perihelion in the year 2000. The stresses induced by perihelion passage are a genuine phenomenon, and comets sometimes do not survive such close encounters. Should 3I Atlas undergo fragmentation, any resulting debris would continue along its existing hyperbolic trajectory, heading out of the solar system. Any dust liberated would then disperse along this path, not necessarily in a direction that would intersect Earth's. Limitations in coronagraph technology, particularly in regions close to the sun, create observational blind spots that can significantly influence public perception. Instruments like Soho's LASCO can observe regions a few solar radii outward, but the area immediately adjacent to the sun remains obscured. The stereo spacecraft, positioned at different vantage points, offer alternative viewing angles, but also have their own coverage limitations. This implies that there are periods, ranging from hours to days, surrounding a comet's perihelion when continuous observation becomes challenging. Images might be received in batches and processed several hours after their acquisition. For those with scientific literacy, these are understood operational constraints. However, for individuals inclined towards conspiratorial thinking, these missing images can be interpreted as evidence of concealed truths. The solar environment is not a mere backdrop. It is the fundamental stage upon which the comet's drama unfolds. Without a comprehension of solar wind, coronal mass ejections, radiation pressure, and sublimation physics, it is impossible to accurately assess whether a comet's behavior is natural or not. Every jet observed, every sudden brightening, and every instance of tail disconnection possesses a tangible physical explanation rooted in plasma physics and thermodynamics. The sun is far more than just a source of illumination. It actively participates in the narrative, exerting forces that push and pull on the comet, shaping its visible appearance, and on occasion producing visual effects that can be easily misinterpreted. Therefore, the central question becomes, is the sun merely altering our perception of 3I Atlas, or is the comet exhibiting some unforeseen behavior under solar influence? To ascertain the answer, we must first understand the observational instruments being employed, their detection capabilities, their limitations, and how these constraints shape the narrative we are able to construct. This naturally leads us to the next segment, Part 8, focusing on the instrumentation, what these instruments observe, and what they do
32
not.
seconds
Every
into the flight.
telescope, every camera, and every
Three
sensor
liquid fuel main
possesses
engines soon will
unique
throttle back to
characteristics,
72% of
a
rated
distinct
performance
set of
down in the
strengths
bucket,
and
reducing the
weaknesses
stress
that
on the
dictate
shuttle as
what
it goes
information it can
transonic.
reveal and what it might overlook. Comprehending these individual traits is paramount for interpreting astronomical data, particularly during events like the perihelion passage of 3I Atlas, where multiple instruments are trained on the same celestial object from varying perspectives and with differing technical specifications. The James Webb Space Telescope, JWST, excels in infrared spectroscopy, a technique that dissects light into its constituent wavelengths, thereby enabling the identification of chemical compositions with remarkable precision. JWST's observations of 3I Atlas provided crucial insights into its carbon dioxide-rich coma because its spectrographs are
T-minus
capable
10,
of resolving
9,
narrow
8,
emission lines
7,
that are indicative
6,
of specific
5,
molecular signatures. However,
3,
JWST is not
1,
designed for rapid
0,
response
and
observation.
liftoff
Its
of
observing
Space
time
Shuttle
must be
and
scheduled
Atlas
weeks in
on mission
advance,
to build,
competing with numerous other
resupply, and
scientific
to do
projects.
research on the
It cannot
International
provide
Space
continuous
Station.
monitoring of a target. Instead, it captures
Houston now controlling,
discrete
Atlantis
snapshots,
begins its
albeit
penultimate journey to shore up the
exceptionally
International
detailed
Space
ones.
Station.
The Hubble Space Telescope offers
Atlantis
high-resolution
now in the
imaging
proper
in the
alignment for its
optical and
8.5-minute
near-infrared
ride to orbit,
spectrum,
4.5 million
meticulously
pounds of hardware
documenting
and
the
humans
structural
taking aim on the
intricacies of the
international
nucleus
outpost.
and coma. Hubble observed 3I Atlas on multiple occasions
30
throughout
seconds into the
September
flight.
and October,
Atlantis
providing
almost 2
records of
miles in
its
altitude,
jet
almost 6
activity
miles
and
downrange from the
rotational
Kennedy Space
period.
Center already, traveling
Nevertheless,
500
Hubble
miles an
also
hour.
has a restricted field of view and must maintain a significant distance
The 3 liquid fuel
from the
main
sun
engines
to
now
prevent
throttling back to
potential damage to
72%
its
of rated
sensitive
performance, going
instruments.
into the bucket,
Strict
reducing the
solar
stress on the
avoidance
shuttle as it
zones are
breaks through the
enforced,
sound
meaning
barrier.
certain geometrical configurations are simply unobservable. Ground-based telescopes such as the Gemini Observatory and the Very Large Telescope, VLT, provide the advantage of observational flexibility and large apertures for light collection, making them invaluable for tracking fainter features and conducting swift follow-up observations. These facilities contributed spectroscopic and imaging data that complemented observations made from space. However, their utility is subject to constraints imposed by weather conditions, daylight hours, and the inability to observe during the day when the comet is too close to the sun in the sky. SOHO's LASCO coronagraphs are the workhorses for observations near the sun. They achieve this by employing an occulting disk to block the bright solar disk, thereby allowing the much fainter corona and nearby celestial objects to be detected. LASCO has successfully observed thousands of comets over its many decades of operation, including numerous instances where comets grazed the sun and did not survive. However, coronagraphs are not without their limitations. They are prone to saturation when exceptionally bright objects traverse their field of view. They also produce artifacts, such as geometric patterns and streaks caused by diffraction and internal reflections. The processing of raw coronagraph data necessitates the subtraction of background coronal light, the removal of cosmic ray impacts, and compensation for instrumental effects, all of which are time-consuming procedures. The stereo spacecraft, strategically positioned at different points in Earth's orbit, provide stereoscopic perspectives of the Sun and the inner solar system. During the perihelion passage of 3I Atlas, one of the stereo satellites offered an advantageous viewing angle. Despite this, communication delays and data downlink schedules meant that acquired images were often received hours after their capture. Geostationary Operational Environmental Satellite, GOES, satellites, primarily utilized for weather monitoring, occasionally capture images of bright comets in their solar imagery. However, their temporal resolution and sensitivity are optimized for solar phenomena, not specifically for comets. Ground-based meteor camera networks operated by organizations such as the American Meteor Society, the International Meteor Organization, and various national agencies employ calibrated all-sky cameras to triangulate meteor trajectories. While these systems are highly effective for meteor detection, they are not capable of directly observing comets. Radar systems can track meteor trails by detecting ionization, providing velocity and trajectory data even during daylight hours. Infrasound arrays are used to listen for atmospheric explosions, offering energy estimates that are independent of optical observations. Now let us delve into the concepts of ephemerides and non-gravitational accelerations. An ephemeris is essentially a table detailing the predicted positions of a celestial object at future points in time, calculated based on the gravitational equations of motion. For 3I Atlas, its ephemeris is publicly accessible through NASA's Horizon system, which accounts for the gravitational influences of the Sun, planets, and larger asteroids to forecast the comet's trajectory. However, comets do not strictly adhere to purely gravitational paths. The process of outgassing generates a thrust, albeit minuscule, which can subtly alter the comet's predicted course. Quantifying these non-gravitational forces requires extensive observations spanning weeks or months to discern the cumulative deviation from a trajectory dictated solely by gravity. This is where speculation regarding deliberate maneuvers enters the discussion, and it is also the reason why such claims are exceedingly difficult to either definitively prove or disprove. Outgassing can indeed mimic the effect of thrust. If a minor change in velocity, denoted as a delta V, is observed, it is not immediately possible to distinguish whether this deviation stems from an asymmetrical jet of gas or from an intentional engine burn. The observed signature would appear similar, a departure from the predicted orbit that accumulates over time. To differentiate between these possibilities, multiple independent datasets would be necessary, demonstrating that the delta V is either too substantial, too precisely directed, or occurs at times inconsistent with patterns of solar heating. It would be essential to rule out all natural explanations with a high degree of certainty, a process that demands extensive modeling and data that might not be promptly released to the public. Let us consider two historical case studies where apparent anomalies were ultimately resolved with the accumulation of additional data. Comet 73P, Schwarzmann-Wachmann. 3 began fragmenting in 1995, producing multiple nuclei that initially led to confusion in trajectory predictions. As more observations became available, the orbital mechanics of each fragment became clearer, and the initial anomaly dissipated. Oumuamua, the first confirmed interstellar object discovered in 2017, exhibited a small non-gravitational acceleration that ignited considerable debate. Following months of analysis, the scientific consensus settled on outgassing as the most probable explanation, although the absence of a visible coma made this particular case unusual. In both instances, phenomena that initially appeared perplexing became explicable with patience and the acquisition of further data. Artifacts from coronagraphs are a perpetual source of misunderstanding. Bright streaks radiating from the occulting disk are optical diffraction patterns, not representations of actual physical objects. Cosmic ray impacts produce bright dots that are only visible in a single frame. Compression artifacts resulting from image processing can manifest as blocky patterns. These are well understood phenomena by instrument scientists, but they can be easily misinterpreted by casual viewers using archived images. A single frame displaying an unusual streak adjacent to 3 Atlas does not imply the presence of a physical object. Rather, it indicates an instrumental feature, and context from adjacent frames, observations from other instruments is required to verify any genuine phenomena. What would be instrumentally required to confirm a deliberate maneuver? Firstly, at least 2 independent instruments would need to detect the identical delta V simultaneously, thereby ruling out errors attributable to a single instrument. Secondly, the magnitude and direction of the delta V would need to be inconsistent with any plausible outgassing model. This necessitates a detailed understanding of the cometary nucleus's size, rotation, distribution of volatiles, and thermal properties. Thirdly, the timing of the maneuver would need to exhibit no correlation with solar heating, meaning it would occur on the comet's night side or during a period of decreasing solar flux. Fourthly, a robust reconciliation would be required, demonstrating that models based solely on gravitational forces combined with outgassing are insufficient to match subsequent observations, thus leaving a residual that necessitates an additional thrust turn. Meeting all these criteria represents a significant challenge, and rightly so. Extraordinary claims demand extraordinary evidence. For journalists and content creators tasked with reporting on such matters, the guidance is straightforward. Require at least 2 independent data sets and ephemeris reconciliation before characterizing any observed event as a maneuver. A solitary coronagraph image exhibiting an anomalous streak does not constitute evidence. A pattern of deviations corroborated by multiple telescopes and irreconcilable with natural models would indeed be compelling. To date, no such definitive pattern has been established for 3I Atlas. Every observed deviation has remained consistent with the anticipated outgassing-driven accelerations for a carbon dioxide-rich comet in proximity to its perihelion. Instruments are powerful tools, but they are
32 seconds into the flight,
and humans interpret
the 3
data
liquid
through
fuel
the
main
lens of
engines soon will
models and
throttle back to
assumptions.
72% of
Raw
rated
data is
performance
not
down in the bucket,
synonymous with
reducing the stress on the
completed
shuttle as it
scientific
goes
understanding.
transonic.
Data only attains the status of science when it undergoes analysis, peer review, replication, and integration into a coherent physical framework. This process is inherently time-consuming, and it is within this temporal gap that misunderstandings and conjecture tend to flourish. Having now examined the physical mechanisms and the instrumentation involved, the next layer to consider concerns the institutions themselves, the agencies and organizations responsible for managing the data and determining its release schedule. What are their motivations? What constraints do they operate under? And could there be reasons beyond mere prudence for the manner in which information is disseminated? This brings us to Part 9, focusing on information strategy and institutional
9,
incentives.
8,
Institutions
7,
are not monolithic
6,
entities.
5,
They comprise individuals
3,
with budgets,
2,
defined mandates,
1,
political pressures,
0.
and competing priorities.
Liftoff of
Organizations
Space
such as
Shuttle
NASA,
Atlantis
the European
on
Space
mission to
Agency,
build,
national
resupply,
observatories,
and to do
university
research
research
on the
groups, and
International
military
Space
space
Station.
surveillance networks all
Houston now
function under
controlling.
distinct
Atlantis
sets of
begins
rules
its
and
penultimate
incentives.
journey to shore up the
Understanding
International
these
Space
underlying
Station.
incentives is crucial for comprehending the dynamics
Atlantis
of
now in the proper
information flow.
alignment for its 8.5
Why
minute
some
line
data
to
is
orbit,
released
4.5
promptly
million
while
pounds
other
of
data
hardware
is
and
delayed,
humans taking aim
and
on the
why
International
perceived gaps
Outpost.
might arise that appear suspicious but are in fact quite ordinary.
30
Firstly,
seconds
it
into
is
the flight.
essential to acknowledge
Atlantis
that
almost 2
institutions
miles in
possess
altitude, almost
legitimate
6 miles
reasons
downrange
for
from the Kennedy
safeguarding
Space
their
Center already,
credibility.
traveling 500 miles
If
an
an
hour.
agency releases preliminary data that is later proven
The 3 liquid fuel main
incorrect,
engines now
it
throttling back to
erodes public
72%
trust.
of rated performance, going
The
into the
incident
bucket,
involving the
reducing the stress on the
faster-than-light
shuttle as it breaks through the
neutrinos
sound
announced
barrier.
by the Opera experiment in 2011 serves as a pertinent example. The reported result was dramatic and had the potential to overturn fundamental principles of physics. After months of rigorous scrutiny, the anomaly was ultimately attributed to a loose fiber optic cable. While the retraction was scientifically necessary and appropriate, it generated considerable ridicule and fostered skepticism toward subsequent announcements. Agencies learn from such experiences, leading them to adopt a cautious approach, sometimes to an excessive degree, because the repercussions of public error are significant. Secondly, institutions must prioritize the avoidance of public panic. Planetary defense policies explicitly aim to balance transparency with the imperative of maintaining public composure. In instances where a small asteroid is detected on a potential collision course with Earth, agencies have established protocols for assessing the threat level before issuing public statements. The Torino scale and Palermo scale are used to quantify impact risks, and public alerts are only triggered for objects exceeding specific thresholds. This is not a practice of secrecy for its own sake, but rather a form of triage. The overwhelming majority of objects that initially raise concerns are subsequently determined to be harmless following refined observations. Announcing every preliminary detection would inevitably result in a constant barrage of false alarms. Thirdly, institutions are compelled to protect sensitive operations. Military space surveillance assets are tasked with tracking satellites, space debris, and potential threats. Some of the data collected by these systems overlaps with civilian astronomical observations. Disclosing the full capabilities of tracking systems, their resolution limits, their coverage areas, or their operational parameters could compromise national security. This creates the inherent tension where valuable data may exist but cannot be fully shared. Civilian agencies might receive sanitized versions of this data, with specific details omitted. This is not indicative of a conspiracy, but rather a matter of operational security, and it is a common occurrence in any domain where military and civilian interests intersect. The typical pathway for the dissemination of major astronomical discoveries follows a sequence: observation, internal verification, peer review, and a staged public release. Internal verification involves scrutinizing observations for instrumental errors, corroborating the findings with independent data sets, and constructing models to explain the observed phenomenon. Peer review entails submitting research findings to a scientific journal, where other experts meticulously evaluate the methodology and conclusions. A staged release encompasses briefing senior officials, preparing press materials, coordinating with international partners, and timing the announcement to coincide with the publication of the research. This entire process can extend over several weeks or months. During this period, the information exists but remains inaccessible to the public, creating an opportunity for leaks, rumors, and speculation to emerge. Now let us introduce a speculative hypothesis, clearly identified as such. Could carefully managed ambiguity serve institutional objectives beyond simple prudence? Consider a scenario where an agency detects something genuinely unusual, but is uncertain about its precise nature. Releasing incomplete information might prompt premature conclusions. Conversely, withholding it entirely risks appearing evasive if leaks do occur. A middle ground might involve staged ambiguity, releasing just enough information to acknowledge awareness without committing to a definitive interpretation. This would allow observers to gauge the public and scientific community's responses, using that feedback to inform subsequent communications. In essence, this approach would transform public discourse into a form of behavioral experiment, testing reactions before full disclosure. This concept is speculative and raises significant ethical concerns. Utilizing public anxiety as a research tool without explicit consent would violate established norms of transparency and respect. Nevertheless, it warrants consideration, as institutional behavior sometimes exhibits patterns consistent with the testing of messages prior to their full deployment. Press releases employing ambiguous language, staged leaks intended to gauge reactions, and delayed clarifications contingent upon the reception of initial information can all align with this model. Whether this represents an intentional strategy or simply bureaucratic friction is impossible to ascertain without access to internal documentation, but the pattern itself is discernible. Budgets allocated for planetary defense and political considerations introduce an additional dimension. Rare events such as the detection of interstellar objects attract significant media attention, which in turn generates public interest and can influence funding decisions. Congress allocates NASA's budget on an annual basis, and high-profile scientific missions often compete with more routine operational needs. A captivating interstellar visitor provides a compelling news hook that budget advocates can leverage to argue for increased telescope funding, extended mission durations, and the development of new detection programs. This creates an incentive to prolong the narrative, emphasizing mystery and potential without resorting to overstatement that could jeopardize credibility. It is a delicate equilibrium. Historical case studies illuminate the spectrum of institutional transparency. When the asteroid 99,942 Apophis was first discovered in 2004, it presented a small but non-zero probability of impacting Earth in 2029. NASA and the ESA maintained transparency regarding this risk, providing regular updates as the orbit was refined and the probability eventually receded to zero. This exemplifies effective transparency. At the other end of the spectrum, certain military satellite observations pertaining to meteors and atmospheric events are classified, with only aggregated statistics being publicly released. The data exists but remain secured behind classification barriers, creating informational voids that fuel conjecture. Legal and regulatory frameworks also play a role. Data collected by government-funded observatories is frequently subject to records laws, but exemptions exist for national security, ongoing research, and proprietary instrument data. University observatories retain ownership of their data and can place embargoes on it until formal publication. International collaborations operate under data sharing agreements that incorporate time delays. None of these practices are inherently nefarious, but they contribute to a complexity that is easily misinterpreted as deliberate obstruction. For viewers attempting to interpret official statements, the following guidance is offered. Language that signals uncertainty typically includes phrases such as preliminary analysis, further observations needed, and models suggest. These phrases indicate genuine scientific caution. Identifying language that signifies concealment is more challenging, as true concealment often manifests as an absence of information rather than evasive wording. If an agency issues a no comment, that is an explicit refusal to provide information. If data is provided but accompanied by significant caveats, it signifies transparency coupled with uncertainty. This distinction is crucial. If data is being managed, the pertinent question then becomes managed for what purpose? Is it to prevent public panic, to safeguard sensitive capabilities, to control the narrative until peer review is complete? Or could there be something genuinely unusual that necessitates careful handling? Without internal access, a definitive answer is unattainable. However, we can map the various possibilities and recognize that multiple motives can coexist. Institutions are inherently complex and their behavior reflects this complexity. Now, having outlined the physical mechanisms, the instrumentation, and the institutional dynamics, we arrive at the most speculative element of this inquiry. What if there is more to 3I Atlas than mere ice and rock? What if someone somewhere is observing it because they suspect it might be observing them back? Let's delve into that notion with meticulous scrutiny and
32 seconds into the flight.
caveat illuminated.
The three
This is
liquid
part
fuel
10
main
of the
engines soon will
segment
throttle back to
dedicated to
72% of rated
speculative
performance down in
and
the
a
bucket,
thought
reducing the
experiment
stress on the
concerning
shuttle as it
Obeth
goes
maneuver
transonic.
and potential colonization of Jupiter. Prepare for an extensive disclaimer. What follows is purely a speculative exercise exploring possibilities with an extremely low likelihood, substantially less than 1%. This is not an assertion, nor is it evidence. Rather, it's an investigation into what might be physically achievable under highly improbable circumstances, presented to illuminate the reasoning some enthusiasts employ when observing objects like 3I Atlas. Everything in this section is explicitly marked as hypothetical, We will revert to confirmed facts at the conclusion. The Obeth maneuver is a genuine concept in orbital mechanics, named after Herman Obeth, a pioneering figure in rocketry. The underlying principle is straightforward. A rocket burn executed within a significant gravitational field, where an object's velocity is at its apex, yields a greater alteration in total
Liftoff, Space Shuttle Atlantis. Mission to build,
this disparity
resupply,
arises
and to do
because
research
kinetic energy
on
is
the International
proportional
Space
to the
Station.
square of velocity.
Houston now
Near the
controlling.
sun,
Atlantis begins its
perihelion,
penultimate
an
journey
object
to shore
achieves
off the International
tremendous
Space
speed
Station.
due to gravitational acceleration. A brief
Atlantis now in the
application of
proper
thrust at
alignment
this
for its
precise
8.5-minute
moment
ride to orbit,
capitalizes on the
4.5 million
heightened
pounds of
velocity,
hardware and humans
resulting
taking
in a
aim on the International
disproportionately
Outpost.
large shift in both trajectory and final velocity when the object is distant
30 seconds
from
into the
sun.
flight,
Interplanetary missions
Atlantis almost
commonly
2 miles in
leverage this
altitude,
principle
almost 6
to
miles
conserve
downrange from the
propellant.
Kennedy Space Center
Now let's
already,
apply
traveling
this
500
concept
miles
to
an hour.
3I Atlas. Hypothetically, if this object were not a
Three liquid
natural
fuel main
comet,
engines
but
now
rather a
throttling back to
spacecraft equipped with
72% of rated
finite fuel
performance going into
reserves,
the bucket, reducing the
perihelion
stress
would
on the shuttle
represent
as
the
it breaks through the
optimal
sound
juncture
barrier.
for executing a trajectory correction. A modest burn during its closest solar approach could recalibrate its outbound path towards a predetermined destination while minimizing fuel consumption. The timing of this perihelion on October 29, 2025, assumes particular relevance if one is seeking indications of deliberate navigation, although timing alone is insufficient proof. Stefan Burns, a researcher and analyst, has thoroughly examined this scenario. He suggests that if 3I Atlas were to execute an Obeth burn specifically targeting the Jupiter system, a hypothetical rendezvous could transpire around March of 2026. The mechanics involved are as follows. The comet's hyperbolic trajectory naturally propels it away from the sun post-perihelion. A precisely timed burn could subtly nudge this outward trajectory towards Jupiter's orbital plane and position, thereby facilitating a gravitational assist or a close flyby. This would necessitate precise knowledge of the required delta V, which itself is contingent upon the object's current trajectory, the desired final trajectory, and the efficiency of the propulsion system. While the calculations are intricate, they remain theoretically within the bounds of plausible propulsion technologies. Why Jupiter specifically? Its Galilean moons, Ganymede, Europa, Callisto, and Io, are regarded as among the most compelling candidates for future colonization or resource utilization within our solar system. Ganymede stands out as the largest moon, possessing its own magnetic field and significant reserves of water, ice. Its diameter measures 5,268 kilometers, and its gravitational pull is approximately 1.4 meters per second squared, roughly 14% of Earth's gravity. Europa, enveloped by an icy shell, harbors a subsurface ocean that may contain more liquid water than all of Earth's oceans combined. It has a diameter of 3,122 kilometers and a gravity of 1.3 meters per second squared. Callisto, meanwhile, exhibits geological stability and experiences considerably lower radiation levels compared to the inner moons. Its diameter is 4,821 kilometers, with a gravity of 1.2 meters per second squared. Io, a body of intense volcanic activity, is likely unsuitable for long-term human settlement, but is abundant in sulfur and other volatile compounds. From a strategic perspective for potential colonization, Ganymede offers size, magnetic protection, and valuable resources. Europa presents the allure of vast water reserves and potential sources of chemical energy. Callisto provides a sanctuary from Jupiter's potent radiation belts. All three of these celestial bodies are situated sufficiently far from the sun that solar power generation would be limited. However, nuclear or fusion-based energy sources could adequately sustain human habitats. The challenges associated with such endeavors are indeed immense, including pervasive radiation, vast distances from Earth, the extreme cold, the detrimental physiological effects of microgravity, and the absence of a breathable atmosphere. Nevertheless, none of these obstacles are inherently insurmountable with the advancement of sophisticated technology. Alternative, low-probability pathways also exist. For instance, a flyby of Mars could be targeted with a different burn profile, potentially leading to an arrival in late 2026 or 2027. Trojan asteroids, gravitationally anchored within Jupiter's orbit at 60 degrees ahead and behind the planet, could serve as intermediate staging posts. However, these require a greater delta V to achieve the same outcome as a direct Jupiter approach, making them less energy efficient. To clearly delineate the epistemic status of these propositions, let us assign illustrative probabilities. The likelihood that 3I Atlas is an artificial construct rather than a natural comet is less than 0.1%. If it were indeed artificial, the probability that it would execute an Obeth maneuver towards Jupiter is less than 1%, conditional on it being artificial. Consequently, the cumulative probability of both these events occurring is substantially below 0.01%. It is crucial to emphasize that these figures are not derived from rigorous calculations, but serve as illustrative placeholders to convey the extreme unlikelihood of this scenario, ensuring it is not mistaken for a plausible expectation. Visual aids for this segment would ideally include overlays depicting hypothetical trajectory adjustments based on what-if ephemerides, diagrams illustrating the Obeth effect through delta V calculations, and individual cards for each Galilean moon detailing their key statistics and advantages or disadvantages for colonization. All such visuals would be prominently watermarked with the word speculative in large lettering. The fundamental objective here is to demonstrate the physical validity of the principles, even if their application to 3I Atlas lacks evidential support. So why engage with such a speculative line of inquiry? Because comprehending the underlying logic empowers us to recognize it when encountered in online discussions. Individuals who analyze 3I Atlas through this speculative lens are not necessarily behaving irrationally. They are applying established physics to an unusual object and posing hypothetical questions. Their reasoning deviates into problematic territory when they interpret the absence of evidence as definitive proof, when they construe every data gap as corroboration, or when their speculation supersedes the null hypothesis, which posits that the object is simply a natural comet. The null hypothesis, the default assumption, is that 3I Atlas is an unexceptional interstellar comet exhibiting predictable cometary behavior as it approaches perihelion. To refute this hypothesis necessitates positive, concrete evidence. Such evidence would include non-gravitational accelerations inconsistent with outgassing, discernible radio emissions, optical signaling, structural characteristics incompatible with natural formation, or trajectory alterations that defy established laws of physics under natural forces. As of now, none of these indicators have been confirmed. Speculation remains exactly that, speculation, until verifiable data compels a reevaluation. The concept of an interstellar object executing a maneuver for potential future exploration is undeniably captivating. The notion that we might be witnessing real-time interstellar navigation is profound. However, until independent observational instruments detect a delta V that cannot be attributed to outgassing, until spectroscopic analysis reveals constituents beyond mere cometary dust, or until trajectory refinements unequivocally demand an artificial explanation. This possibility remains firmly within the domain of science fiction, and that is perfectly acceptable. Science fiction often poses the very questions that scientific inquiry eventually seeks to answer. The critical distinction lies in not conflating the question with the answer. Now let us pivot back to concrete realities and examine the technologies and discoveries that are actively reshaping our methods of astronomical observation. Because regardless of whether 3I Atlas proves to be a comet or something more, the instruments we are currently developing will ultimately provide an irrefutable answer. This leads us to Part 11, Quantum Sky Maps, Entanglement and Timing Breakthroughs. The resolution of cosmic enigmas frequently hinges on the ability to achieve exceptional precision. How accurately can one determine the trajectory of a meteor? How precisely can an observation be time-stamped? How can data from multiple telescopes potentially separated by thousands of kilometers, be perfectly synchronized. Until very recently, these crucial questions were constrained by the limitations of classical technology. Atomic clocks, while capable of synchronization to microseconds, fell short for certain transient phenomena where nanosecond precision is paramount. This landscape is undergoing a significant transformation. Quantum timing systems leveraging entangled photons and optical lattice clocks are now achieving synchronization accuracies measured in picoseconds or trillionths of a second. Research initiatives across Europe, the United States, and China have successfully demonstrated quantum clock networks that maintain temporal coherence across fiber optic links extending for hundreds of kilometers. The implications for astronomical observation are nothing short of revolutionary. When observations
32 seconds into the flight.
with sub-nanosecond
3 liquid
precision
fuel main
across a
engines soon will
distributed
throttle
network,
back to
it becomes
72% of rated
possible to
performance down in the
triangulate
bucket,
transient
reducing the
events
stress on the
with
shuttle as it goes
unprecedented
transonic.
accuracy. Consider the triangulation of meteors. Currently, all sky cameras operated by the American Meteor Society utilize GPS timing, which offers an accuracy of approximately 10 nanoseconds. This level of precision enables trajectory reconstruction with uncertainties of several hundred meters in altitude and a few degrees in angular direction. With the advent of quantum timing, these uncertainties are projected to diminish by orders of magnitude. This would allow for the detailed resolution of not only an object's trajectory, but also its rotational state, surface irregularities, and fragmentation dynamics with exquisite fidelity. For a swift meteor event lasting a mere 2 seconds, nanosecond timing translates to the ability to resolve thousands of independent data points, as opposed to the hundreds with current methods. To track an object such as 3D
Liftoff of Space Shuttle
timing
Atlantis
unlocks
on a
even
mission
more
to
powerful
build,
capability.
resupply, and to do
Coherent
research
multi-station
on the International Space Station.
interferometry. By synchronizing radio
Houston now
telescopes or
controlling.
optical
Atlantis begins
telescopes
its
to quantum
penultimate journey to
precision,
shore up the
their
International
signals
Space
can be
Station.
combined, effectively creating a single instrument
Atlantis
with a
now in proper
baseline
alignment
equivalent
for its
to the
8.5
distance
minute ride to
separating the
orbit,
stations.
4.5 million pounds
This
of hardware
technique,
and
already
humans taking
established
aim
in
on the
radio
International
astronomy through
Outpost.
very long baseline interferometry, VLBI, is becoming
30 seconds
viable
into
in
the
the
flight.
optical domain thanks
Atlantis
to
almost 2
quantum
miles in
clocks.
altitude, almost
The
6
angular
miles downrange
resolution
from the Kennedy
attainable
Space
would
Center, already
facilitate the
traveling
direct
500 miles
imaging
an hour.
of the nuclear structure of a comet located millions of kilometers
The 3
away.
liquid fuel main
The
engines now
practical
throttling back to
implementation for
72% of
observatories
rated
embracing
performance, going
quantum
into the bucket,
timing
reducing
involves
the stress on the
substantial
shuttle as it
hardware
breaks through the
upgrades,
sound barrier.
the establishment of robust network infrastructure, and the development of meticulous calibration protocols. Quantum clocks, being both costly and delicate, necessitate laser-cooled atoms maintained within ultra-high vacuum environments. Distributing the quantum time signal across a network requires specialized fiber links or free space optical communication systems capable of preserving quantum entanglement. The current expenditure for each node can run into the millions of dollars. However, as with all burgeoning technologies, prices are expected to decline as adoption rates increase. A significant philosophical implication arises from this technological advancement. Superior instruments fundamentally alter what constitutes evidence. With classical timing, an uncertainty of plus or minus 1 kilometer in trajectory might permit multiple interpretations of a meteor's origin. Quantum timing, by reducing this uncertainty to plus or minus 10 meters, collapses these interpretations into a single, definitive answer. Ambiguity in this context is not an inherent characteristic of nature, but rather a reflection of measurement limitations. As these limitations dissolve, so too does the scope for speculative interpretation. Envision a future event akin to the Moscow fireball, observed with globally distributed cameras synchronized by quantum means. The resulting data set would encompass a precise three-dimensional reconstruction of the entire trajectory, an assessment of the ablation rate as a function of altitude, a microsecond resolution analysis of the fragmentation sequence, and a spectral evolution revealing compositional changes as different layers of the meteoroid ablate. This represents not merely an increase in data quantity, but a qualitative leap in scientific understanding. For 3I Atlas and other future interstellar visitors, quantum timing could definitively determine whether Minor orbital deviations are attributable to outgassing jets, tidal forces, or some other mechanism. If a delta V event precisely coincides with perihelion passage down to the nanosecond, this would strongly support a thermal outgassing mechanism. Conversely, if such an event occurs off-peak with no correlation to solar heating, it would necessitate an alternative explanation. The precision required to differentiate between these scenarios is now within reach. The universe's secrets will become increasingly difficult to conceal as our timing accuracy improves. Nature operates independently of our measurement tools, yet our capacity to interpret natural phenomena is intrinsically dependent upon them. Timing, however, is not the sole frontier where technological advancements are revolutionizing astronomy. Artificial intelligence is now actively participating in the discovery process itself, identifying transient events with a speed that far surpasses human capabilities. Yet this accelerated pace introduces its own set of challenges, particularly when the AI's judgment is imperfect and the ramifications of its errors are amplified by social media. This brings us to part 12, AI astronomers, autonomous discovery, and the explanation gap. Something fundamentally shifted in the field of astronomy this year, a change that largely went unnoticed by the public. The observers of the cosmos are no longer exclusively human. On October 15, 2025, the Vera C. Rubin Observatory in Chile discreetly activated its anomaly recognition and triage engine, an artificial intelligence system engineered to autonomously scan the celestial expanse and flag any unusual phenomena without initial human oversight. Within 48 hours, it had identified 3,217 transient events. By the week's conclusion, this number had surpassed 10,000. The system operates continuously, 24 hours a day, 7 days a week, processing approximately 15 terabytes of image data nightly. It never falters, never fatigues, and never second-guesses its own conclusions. It discerns patterns in the darkness that would require human eyes months to detect if they were detected at all. We have now entered the era of the autonomous astronomer, where machines dictate which cosmic anomalies warrant our attention and which are relegated to obscurity. The pertinent question that appears to be largely unaddressed is what happens when the algorithm errs. Allow me to elucidate the operational principles of these systems, as understanding their inner workings is crucial for discerning whether an observation signifies genuine strangeness or merely algorithmic misinterpretation. Modern transient detection pipelines typically follow a three-stage methodology. Firstly, telescopes capture extensive wide-field images of the sky, often encompassing hundreds of square degrees in a single exposure. Secondly, specialized software meticulously subtracts previous images from the newly acquired ones, thereby isolating any alterations, appearances, or brightening events that have occurred since the last observation. Thirdly, and this is where artificial intelligence plays a pivotal role, machine learning models evaluate each identified transient and assign it a specific classification: supernova, asteroid, satellite, glint, instrumental artifact, or an unknown category. The system then determines which of these objects merit further observation by telescopes globally. No human intervention is involved in this initial classification process. The AI makes the definitive call, initiates alerts, and the global astronomical network mobilizes in response. This automated process occurs thousands of times each night. The advantages are undeniably revolutionary. These systems process data at speeds that would necessitate an army of graduate students working ceaselessly for decades. They are adept at recognizing subtle patterns in light curves, spectral signatures indicative of exotic stellar explosions, and orbital perturbations suggesting the presence of previously undiscovered objects in the outer solar system. The AI is immune to confirmation bias and fatigue-induced errors. It diligently scans every patch of sky, without neglecting areas where nothing significant has historically occurred, consistently and without exception. For genuine scientific discovery, this represents an unparalleled advancement in observational capability We are now identifying supernovae before they reach peak luminosity, detecting asteroids posing collision risks weeks earlier than human-led surveys could, and mapping the dynamic sky with a resolution that seemed unattainable nearly 5 years ago. However, this efficiency carries a consequential downside, one that grows more pronounced with our increasing reliance on these systems without fully grasping their inherent limitations. Machine learning models are intrinsically dependent on the quality and comprehensiveness of their training data, which is inherently biased by prior human observations and classifications. If the AI has not been exposed to a particular type of phenomenon, it will either misclassify it or categorize it as unknown. This unknown designation may or may not trigger human review, contingent upon the system's configuration. This introduces critical blind spots, perceptual lacunae, where genuinely novel phenomena could be systematically overlooked simply because they do not conform to any pattern the algorithm has been trained to recognize. Even more alarmingly, the AI can generate false positives, flagging mundane events as extraordinary due to subtle data anomalies that bear no relation to actual cosmic occurrences. These anomalies can include satellite glints, atmospheric distortions, detector noise, or software glitches. Any of these can confound the algorithm if they manifest in unexpected ways. Let me present a hypothetical scenario that vividly illustrates how rapidly such a situation can escalate out of control. Imagine the AI flags an unusual brightening event in proximity to Jupiter's orbit. The light curve exhibits a peculiar pattern, flickering in a manner unfamiliar to the algorithm. The system automatically dispatches an alert to the Astronomer's Telegram, a public forum where professional astronomers share breaking discoveries. Within minutes, amateur astronomers worldwide begin directing their telescopes toward the specified coordinates. Within an hour, someone captures a screenshot of the alert and disseminates it across social media with the caption, "Unidentified object near Jupiter exhibiting erratic behavior. Professional astronomers investigating." A prominent science influencer boasting 2 million followers encounters this post. They amplify it with their own commentary, speculating about
32
artificial
seconds into the
origins.
flight.
Suddenly, the narrative
3
is
liquid fuel
trending.
main engines
News
soon will
outlets
throttle
seize
back to
upon the story.
72% of rated
Cable
performance down in
networks
the
feature
bucket, reducing the
segments
stress on
debating
the
the
shuttle as it goes
possibility of an
transonic.
alien probe detection. All of this transpires in under 6 hours, predating any opportunity for a professional astronomer to request follow-up spectroscopic analysis or to verify the detection using an independent instrument. By the time a scientific consensus emerges, attributing the event to a combination of a satellite glint and a detector artifact, the narrative has already irrevocably spread. Millions of individuals will firmly believe that something extraordinary transpired near Jupiter. No amount of subsequent correction will entirely erase that initial impression. This is not a far-fetched paranoid fantasy. It represents a plausible sequence of events given the current velocity of information propagation in our media landscape and the minimal friction between automated alerts and their public dissemination. This hypothetical scenario unfolds as follows.
0.
AI detection
Liftoff of Space Shuttle
Automated alert
Atlantis.
posted at
On mission
hour
to build,
0.5.
resupply,
Social
and to do
media
research on the
amplification
International
by
Space
hour
Station.
1. Influencer endorsement
Houston
by
now
hour
controlling.
3.
Atlantis begins its
Mainstream
penultimate
media
journey
coverage
to shore up the
by
International
hour
Space
6.
Station.
Scientific verification by hour
Atlantis
24.
now in the proper alignment for its
Correction
8.5-minute
published
ride to
by
orbit,
hour
4.5
48.
million pounds of
The
hardware and
inherent
humans
problem
taking aim
is
on the
evident.
international
The narrative
outpost.
gains momentum and escapes before the scientific analysis can catch up.
30
Once a
seconds into the
story
flight,
achieves critical mass,
Atlantis almost
factual
2 miles in
accuracy
altitude, almost
often
6 miles
becomes
downrange from
secondary
the
to the
Kennedy Space Center,
emotional
already
resonance
traveling
of the
500
belief.
miles an hour.
Now consider the 3-eye atlas situation through this
The 3
framework,
liquid fuel main
and
engines
suddenly
now
many
throttling back to
aspects begin to make
72%
more
of rated
sense, do
performance,
they
going
not?
into the bucket,
During
reducing
the
the stress
period
on the
when
shuttle as it breaks
anomalous
through the sound barrier.
observations were being reported, multiple automated detection systems were operating at peak capacity, diligently scanning for transient events, flagging unusual brightening phenomena, and posting alerts to public databases without any mandatory human review. If even a single one of these systems misclassified a mundane event as something extraordinary, and that alert reached the appropriate amplifier at the opportune moment, the stage is set for a rapid dissemination of a narrative that may appear conspiratorial, but is in reality a consequence of algorithmic confusion interacting with social media dynamics. This scenario does not necessitate any intentional deception or fabrication of data. It merely requires a machine error amplified by the Internet's propensity to transform uncertainty into a wildfire of speculation. The policy implications arising from this are far from abstract. Who bears the responsibility for vetting AI-generated alerts before they are publicly released? Should there be a mandatory human verification process for specific categories of detections, particularly those involving unusual behavior from high-profile objects like interstellar visitors? What threshold of confidence should an AI be required to demonstrate before triggering a public alert? How do we strike a balance between the speed advantages offered by automation and the risks associated with premature or inaccurate information reaching mass audiences? These are not hypothetical dilemmas. They are critical decisions that observatories and survey teams are actively making at this very moment, often without public consultation or standardized protocols. Fortunately, technical mitigation strategies exist that we could implement if we chose to do so. The adoption of multi-model consensus, where several independent AI systems must concur on a classification before an alert is issued, would significantly reduce the incidence of false positives. Implementing human verification gates for high-impact detections would introduce a crucial layer of sanity checking before information is released into the public domain. The provenance of each alert is annotated with metadata detailing the detection methodology. A confidence score and verification status would equip downstream users with the necessary context to evaluate trustworthiness. While none of these approaches are flawless and will introduce delays that some researchers propose, the alternative is our current system, which prioritizes speed over precision. When this system errs, the repercussions extend far beyond the astronomical community. We must confront the stark reality. Artificial intelligence will uncover more peculiarities, not fewer. As these systems advance, encompassing broader swathes of the cosmos, with heightened observational frequency, the volume of anomalies flagged will escalate dramatically. A majority will prove to be spurious alerts or instrumental anomalies. Some will represent genuine discoveries capable of reshaping our understanding, and a select few will remain truly enigmatic, defying easy categorization as either readily explained or demonstrably extraordinary, residing in that unsettling interstice where scientific inquiry meets the unknown. Society must determine how to interpret this deluge of automated discoveries. The framework we establish now will dictate whether we navigate this transformation with sagacity or descend into cycles of unfulfilled anticipation and disillusionment that undermine public faith in scientific endeavors. Section 13, a solar science landmark featuring the solar orbiter, its polar data, and surprising cycle revelations. We need to address the sun, as nothing transpires within our solar system without its implicit consent. On September 23, 2025, the European Space Agency's Solar Orbiter spacecraft concluded its inaugural high-inclination transit over the sun's southern pole, capturing unparalleled imagery of the magnetic field configurations that dictate our star's behavior. The probe's findings astonished solar physicists, who believed they had a firm grasp on the 11-year solar cycle. The magnetic field lines emanating from the polar regions did not conform to predictions. They exhibited greater disorder, increased dynamism, and a heightened propensity for abrupt realignment than any model had suggested. This has ramifications for comets, for Earth's atmosphere,
32
for every
seconds into the
optical
flight.
observation we conduct of
The
the
three liquid
celestial
fuel main
sphere,
engines soon will
and
throttle
for
back to
discerning whether the
72% of rated
unusual
performance down in the
phenomena
bucket,
witnessed
reducing
by
the stress on the
individuals
shuttle
are
as it goes
genuinely
transonic.
anomalous or merely the sun exhibiting capriciousness. Allow me to provide the context that elevates this discovery to such significance. The sun is not merely a quiescent orb of nuclear fusion. It is a turbulent dynamo of plasma interwoven with magnetic fields that invert their polarity approximately every 11 years. During solar maximum, the apex of this cycle, the incidence of sunspots increases, solar flares become more common, and coronal mass ejections, which are colossal expulsions of magnetized plasma, erupt into space with amplified intensity and frequency. Conversely, during solar minimum, the sun enters a period of relative tranquility. We are currently progressing towards the next solar maximum,
T-minus 10,
anticipated
9,
to reach its
8,
peak in
7,
late 2025,
6, 5,
early 2026,
3,
signifying an escalation in solar
1,
activity. The
0.
data from solar orbit
Lift off
that this
of
cycle
Space
may
Shuttle
prove
Atlantis.
more energetic
Mission
and
to
unpredictable
build,
than
resupply,
recent ones,
and to do research
with consequences
on the
that
International
resonate
Space
throughout
Station.
every region of the heliosphere.
Houston now controlling.
Herein
Atlantis
lies the
begins
reason
its
this is
penultimate
critical
journey to
for
shore up the
comets and why
International Space
neglecting
Station.
solar context when examining Comet CC
Atlantis now in the proper alignment for its 8.5-minute
2024-X1,
ride to orbit.
nicknamed
4.5 million
Thorne-Jitkov
pounds of hardware
object,
and humans
would
taking aim on the
constitute
international
scientific
outpost.
negligence. Comets are fragile entities, loosely aggregated masses of ice,
30 seconds
dust, and
into the flight.
organic compounds
Atlantis
bound by
almost
their
2 miles in
own
altitude,
negligible
almost 6 miles
gravitational pull.
downrange from the Kennedy Space
As the
Center,
comet
already
nears the
traveling
sun,
500
solar
miles an
radiation
hour.
warms its nucleus, inducing the sublimation of
The
volatile
3 liquid fuel main
substances that
engines now
stream
throttling back to
outwards,
72% of
forming the
rated
coma
performance,
and
going into
tail
the bucket,
observable
reducing
from
the
Earth.
stress on the shuttle as it breaks through the
However,
sound
heat
barrier.
is not the sole driver of this process. The solar wind, a continuous outflow of charged particles propagating from the sun at speeds exceeding 1 million miles per hour, also plays a crucial role. The pressure exerted by this wind, combined with the embedded magnetic fields, shapes the comet's tail and influences the extent of material loss during its closest approach to the sun, known as perihelion. When the sun is more active, with more frequent coronal mass ejections and a more tempestuous solar wind, comets endure more severe conditions. They may exhibit unexpected luminosity increases, develop asymmetrical tails, or even fragment if the stresses surpass their structural integrity. The temporal sequence is illustrative. Between mid-September and late October 2025, solar activity surged. We documented 17 M-class solar flares, which are eruptions of medium intensity, and 3 X-class flares, the most potent category. Multiple coronal mass ejections were detected, several of which impacted Earth, triggering geomagnetic storms potent enough to produce auroras, visible at latitudes significantly further south than their typical range. Residents of Texas witnessed the northern lights. Individuals in southern Europe captured images of shimmering curtains of green and red. This was not a subtle phenomenon, it was the sun demonstrating its power, and every celestial body within the solar system felt its effects. Thorne-Jitkov object, which was approaching perihelion during this precise interval, was enveloped by an unusually turbulent solar environment. Any observed brightenings or unexpected alterations in its coma or tail structure must be assessed against this backdrop of heightened solar activity before we resort to invoking esoteric explanations. Solar weather not only directly impacts comets, but also complicates our ability to observe them accurately. Transient scintillation, the rapid shimmering of light as it traverses turbulent plasma, can create the illusion of variability in brightness unrelated to the actual source. Ionospheric disturbances caused by charged particles impacting Earth's upper atmosphere can refract radio waves and introduce artifacts into radar observations. Even optical telescopes are not immune. Atmospheric seeing conditions deteriorate during geomagnetic storms as the upper atmosphere heats and becomes more agitated. This implies that during the very period when Thorne-Jitkov object was most active and of greatest interest, the conditions for its clean observation were het there nadir. Some of what observers perceived may have represented genuine changes in the comet, while other observations could have been due to solar interference with our view. Disentangling these influences necessitates rigorous analysis, not conjecture. Let me offer a simplified guide for determining when to suspect solar-induced anomalies versus authentic cometary alteration. Firstly, consult the Solar Activity Index for the date of observation. If a solar flare or coronal mass ejection occurred within the preceding 24 to 72 hours, regard any brightening or structural shifts in the comet with caution. Secondly, seek corroboration from multiple instruments operating across different wavelengths. If the anomaly is discernible in both optical and radio observations, it is more likely to be authentic. If it appears in only one data set, suspect instrumental or environmental factors. Thirdly, examine ionospheric data. If the ionosphere was disturbed during the observation period, radio and certain optical data may be compromised. Fourthly, compare observations from disparate geographical locations. Solar-induced artifacts frequently affect one hemisphere more than another. Therefore, if observers in Australia report a phenomenon that observers in Europe do not, this serves as an indicator of environmental influence rather than source variability. The solar orbiter findings introduce an additional complexity to this enigma. The chaotic nature of the polar magnetic field suggests that the solar wind is less uniform and more intricately structured than we had presumed. This implies that comets might encounter localized zones of intensified or diminished solar wind pressure, leading to fluctuations in brightness that appear mysterious, but are simply the comet traversing invisible boundaries within the heliosphere. Imagine navigating through fog patches on a highway. Your visibility fluctuates dramatically from one moment to the next, not due to a malfunction of your vehicle, but because you are moving through a structured environment. Comets experience a comparable phenomenon, except the fog is composed of magnetized plasma, and the boundaries are in constant flux. Understanding the sun is not a tangential concern. It is the foundational context, the baseline, the bedrock upon which all subsequent interpretations must be built. When questions arise regarding whether Thorne-Zhitkoff object exhibited unusual behavior, the scientifically responsible response is, unusual compared to what? Compared to comets observed during solar minimum? Compared to comets with analogous orbits and compositions? Compared to models that presuppose a stable solar wind? Each of these comparisons yields a distinct conclusion, and none are valid without factoring in the specific solar conditions prevailing during the observation window. The sun commands the loudest voice in the solar system, and if we fail to heed its pronouncements, we will misinterpret every subtle communication from the objects traversing its domain. Herein lies the aspect that causes me concern. The forthcoming solar maximum is projected to be more vigorous than the last few cycles, potentially the most active in decades. This portends an increase in geomagnetic storms, more frequent auroras at atypical latitudes, greater disruption to satellite operations and communication networks, and amplified opportunities for ordinary solar-driven phenomena to be misconstrued as extraordinary. If individuals are already predisposed to perceive unusual occurrences in the sky, if the prevailing cultural narrative favors an expectation of anomaly, then every solar flare that produces a spectacular aurora, every coronal mass ejection that induces atmospheric luminescence, every ionospheric disturbance that generates peculiar radar echoes, all of these will be filtered through a lens of suspicion and wonder, rather than understood as the sun performing its natural functions. The risk is not that the sun will do something unprecedented. The risk is that we will neglect to account for its actions and mistake its routine ferocity for something far more enigmatic. Section 14, Synthetic Skies, Holography, Volumetric Displays, and the Blue Beam Controversy. At the Consumer Electronics Show in Las Vegas in January 2025, a Japanese company named Sky Canvas presented a demonstration that captivated onlookers. Utilizing a network of micro-drones equipped with synchronized LED arrays, they projected a three-dimensional representation of a phoenix ascending from the desert floor, visible to spectators over a radius of half a mile. The avian figure flapped its wings, shedding embers that lingered in the air before dissipating. For 30 seconds, the illusion appeared strikingly real. Later that spring in Tokyo, another firm unveiled a laser plasma system generating luminous points of light in midair by ionizing atmospheric nitrogen with focused femtosecond pulses. They showcased the technology by inscribing kanji characters 50 meters above the city skyline, their forms shimmering and flickering like luminous calligraphy. Furthermore, in geostationary orbit, at least 2 private aerospace corporations are reportedly developing satellite-based projection systems intended for advertising purposes, designed to cast corporate logos and messages across the night sky using reflected sunlight and synchronized mirrors. The era of synthetic skies has dawned, and the pertinent question is no longer whether we can conjure atmospheric illusions, but rather how convincing these illusions can be and whether they are being employed for purposes beyond mere entertainment. Let me be exceptionally clear regarding the technically achievable capabilities as of 2025. The chasm between cinematic fantasy and engineering reality is narrower than many suppose, though still substantial. Large-scale volumetric displays employing drones or suspended LED matrices can generate impressive localized illusions, observable from specific vantage points and effective within a radius of a few miles at most. Laser plasma systems can produce brilliant points of light by ionizing air molecules, but they demand immense power, direct line-of-sight targeting, and clear atmospheric conditions. Their resolution's limited, their illumination ephemeral, and their geographic coverage restricted. Concepts for satellite-based projection remain largely theoretical, hampered by the energy requirements to deliver adequate luminosity from orbital altitudes and the challenge of overcoming atmospheric scattering. True planet-wide sky projection, the kind envisioned in conspiracy narratives and referencing Project Blue Beam, remains impractical with current technology. It is not inherently impossible, but rather prohibitively expensive, logistically complex, and readily detectable by appropriate instruments. However, here lies the
32
uncomfortable
seconds
truth
into the
at the
flight.
heart of this discussion.
The 3 liquid fuel main
Localized,
engines soon will
high-fidelity
throttle back to
illusions
72%
are
of rated
approaching
performance down in the
feasibility
bucket,
for
reducing the
targeted
stress on the shuttle as it goes
entertainment
transonic.
venues, advertising campaigns, political theater, and even psychological operations could deploy these technologies in ways that deceive local observers, while leaving no discernible trace for distant analysis. Imagine a system capable of projecting a convincing aerial anomaly above a city for 15 minutes, ample time for hundreds of individuals to capture it on their mobile devices, only to vanish before professional instrumentation can be deployed. The resulting videos would proliferate online. Experts would scrutinize the footage, finding no overt indications of digital manipulation because the phenomenon was physically real, albeit artificially generated. The ensuing debate would erupt, with one segment of the internet asserting extraterrestrial origins and another claiming a Neither side would possess definitive proof, and the very ambiguity would become the narrative,
Space Shuttle
evolving
Atlantis.
into a cultural
Mission to
phenomenon that eclipses
resupply,
any
and to
mundane
do research
explanation that
on
might
the
eventually
International
emerge.
Space Station.
The psychology of spectacle
Houston now
magnifies the
controlling.
impact far
Atlantis
beyond
begins its
technological
penultimate journey to
capacity
shore
of
up
the
the
system
International
itself.
Space Station.
Human perception is susceptible to
Atlantis now in
suggestion,
proper alignment for its
particularly
8.5-minute
when
ride to orbit,
encountering
4.5 million
phenomena
pounds of
outside
hardware and
ordinary
humans
experience.
taking aim on the
If you
international
witness
outpost.
something luminous in the sky, behaving in a manner you cannot immediately
30
comprehend,
seconds into the
your
flight,
mind will gravitate
Atlantis
towards
almost 2
familiar
miles in
narratives to
altitude,
make
almost
sense
6
of it.
miles
And in
downrange from the Kennedy Space Center
2025,
already, traveling
these
500
narratives
miles
are
an
shaped
hour.
by decades of science fiction, conspiracy theories, and a
3 liquid
pervasive
fuel main
cultural
engines now throttling
fascination
back
with
to
the notion of
72%
not
of
being
rated
alone.
performance going into the
A
bucket, reducing the
mediocre
stress on the
illusion
shuttle as it breaks through the
strategically
sound
deployed
barrier.
with appropriate framing can engender a global narrative that takes on a life of its own, independent of the original event. The technology need not be perfect. It simply requires sufficient convincing power to surpass the initial threshold of plausibility, and the internet will disseminate the rest. Distinguishing between capability and intent is paramount here, as possession of a technology does not automatically imply its use for nefarious purposes. We possess the technical capacity to create localized aerial illusions. This is an established fact. It does not logically follow that governments or corporations are routinely employing these systems to manipulate public perception. The leap from possibility to certainty requires evidence, and such evidence is conspicuously absent from most discussions concerning synthetic skies. What we have instead is speculation superimposed upon potential, generating a veil of suspicion that obscures the actual technological landscape. Yes, these technologies exist. Yes, they could theoretically be misused. No, there is no credible documentation of their large-scale deployment for deceptive purposes. The absence of evidence is not evidence of absence, but it also does not grant license to assume the worst without data. So how can you, as a reasonably informed individual striving to comprehend what you observe in the sky, ascertain whether something is artificial or natural? Here's a practical checklist. First, seek multi-angle corroboration. If a phenomenon is genuine, multiple observers at different locations should perceive it from varying perspectives, and these perspectives should exhibit geometric consistency. If the phenomenon is a localized projection, its appearance will fluctuate dramatically depending on the viewing angle, or it will only be visible from a specific region. Second, check for cross-verification by instruments. Natural phenomena manifest across multiple wavelengths and detection methodologies. If something is visible in optical light but undetectable by infrared cameras, or if it registers on photographic film but not on digital sensors, suspect an artificial origin or an instrumental artifact. Third, look for spectral inconsistency. Natural light sources, whether astronomical or atmospheric, possess characteristic spectra resulting from their physical emission processes. Artificial sources often exhibit sharp, unnatural spectra dominated by specific wavelengths corresponding to LEDs or lasers. Spectroscopy can instantly differentiate between them. The blue beam conspiracy theory, for those unfamiliar, posits that governments or clandestine organizations will utilize holographic projection technology to orchestrate false flag events in the sky, potentially simulating an alien invasion or religious apparitions for manipulative purposes. This narrative, deeply rooted in Cold War paranoia and Y2K anxieties, persists because it resonates with legitimate concerns about media manipulation and the erosion of a shared reality. The issue is that the theory significantly overestimates the capabilities of current projection technology while underestimating the logistical challenges of orchestrating deception on such a grand scale. Could localized illusions be deployed for propaganda or distraction? Absolutely. Could a global, high-fidelity holographic deception be executed without detection? Not with 2025 technology, and likely not for many decades. What concerns me is not the grand conspiracy, but rather the smaller-scale, opportunistic utilization of these technologies in ways that erode trust and amplify confusion. A corporation testing a new advertising platform without adequate disclosure. A political faction staging a provocation to discredit adversaries. A prankster with access to drones and LED arrays creating a viral sensation for attention. None of these require vast resources or clandestine government programs. They simply necessitate motivation, modest technical proficiency, and an understanding of how narratives propagate in the digital age. The cumulative effect of dozens or hundreds of minor deceptions could be as corrosive to public trust as a single grand conspiracy, and far more challenging to detect or counteract. Technology can amplify belief, but technical limitations remain significant. We are entering an era where the tools for creating convincing illusions are becoming more accessible. However, we have not yet reached an era where these illusions are indistinguishable from reality across all detection modalities. The gap is narrowing, but it has not yet closed. Vigilance is warranted, paranoia is not. The challenge lies in maintaining skepticism without succumbing to cynicism, demanding evidence without dismissing possibility, and recognizing that the most perilous illusions may not be those projected into the sky, but rather those we impose upon ambiguous events due to an inability to tolerate uncertainty. Section 15. Reflection and the new epistemology, coexisting with cosmic uncertainty. Thus we arrive at this juncture, having traversed 15,000 words of intricate exploration, and it is time to step back and ascertain what we have truly gleaned. Our journey commenced with meteor clusters and emerald fireballs illuminating skies from Moscow to Manila. Reports proliferated more rapidly than explanations, and speculation solidified into certainty before the data could provide substantiation. We examined Thorne-Zhitkov object, an interstellar traveler whose approach to the sun coincided with an increase in anomalous sightings. And we posed the question, does this correlation imply causation, or is it merely the universe reminding us that coincidence is not conspiracy? We delved into the limitations of our instruments, the distortions introduced by atmospheric turbulence and quantum timing jitter, and the lacunae in our data pipelines where crucial observations dissolve into bureaucratic limbo. We entertained speculative hypotheses ranging from debris clouds of unidentified objects to autonomous artificial intelligence systems amplifying false positives, and from solar weather complicating observations to synthetic sky technologies probing the boundaries of plausibility. And now, at the conclusion of this odyssey, we must confront the most unsettling query of all. How do we navigate the vast unknown when our societies crave definitive answers? When digital systems amplify confusion, every celestial anomaly sparks a debate about fundamental truth. Let us clarify what we definitively understand. This is the solid ground beneath the shifting sands of speculation. The object designated 3E Atlas is a verifiable entity, corroborated by numerous astronomical facilities. Its orbital path has been meticulously charted. Its closest approach to the sun, its perihelion, has been documented in established scientific publications. The observed meteor events are genuine occurrences, captured on film, cataloged in databases, and witnessed by thousands of individuals who are not experiencing delusions or participating in a coordinated deception. The advanced technological capabilities we have discussed, from artificial intelligence for transient event detection to volumetric displays, are fully functional and in operation, deployed in observatories and showcased at industry exhibitions. The polar data from the Solar Orbiter mission is accurate, revealing magnetic interactions that challenge prior scientific models. These are the concrete facts, the underlying structure of this narrative, the framework supporting all other interpretations. Now let us examine our speculative theories. These are possibilities that might explain observed correlations but lack conclusive evidence. The notion that 3E Atlas could have created a trail of debris through an oath-effect slingshot mechanism is plausible but unproven. It represents a theoretical exploration that aligns with physics but has not been validated by direct observation. The idea that artificial intelligence systems might have miscategorized ordinary events, thereby propagating incorrect information, is consistent with how these systems function, but has not been confirmed in this specific instance. The hypothesis that solar activity contributes to some of the observed brightening anomalies is supported by the temporal coincidence, but not by detailed spectroscopic analysis. The proposition that localized synthetic atmospheric technology could generate convincing, illusory phenomena is technically feasible, but lacks evidence within the context of these specific sightings. These are hypothetical scenarios, conceptual models, interpretive frameworks for ambiguous data,
into the flight,
but they are not established
the 3 liquid fuel main engines
Conflating
will
the
throttle
two
back to
leads to the
72%
demise
of
of
rated
reasoned
performance
inquiry
down in the bucket,
and the
reducing the
triumph
stress on
of
the shuttle as it
unfounded
goes
belief.
transonic.
The central philosophical quandary is this: how can we, as individuals and as a collective, coexist with persistent cosmic ambiguity when our innate psychology craves certainty and our media landscape often penalizes uncertainty? We are not inherently equipped for intellectual humility. Our minds are sophisticated pattern recognition engines, optimized for survival rather than for nuanced understanding. Consequently, our brains will readily invent explanations to fill informational voids rather than tolerate the discomfort of not knowing. This tendency served us well in our evolutionary past, where assuming a rustling in the grass indicated a predator could mean the difference between life and death, even if it was merely the wind.
8, 7.
However, this is
6,
detrimental to
5,
the exploration of the cosmos,
3,
where our knowledge
2,
gaps vastly
1,
exceed our comprehension,
0,
and where premature
liftoff
conclusions
of
based on
Space Shuttle
ambiguous
Atlantis.
data can result in
Mission to
cascading
build,
errors and
resupply,
undermine scientific
and to do
progress
research
and
on the
erode
International
societal
Space
consensus.
Station.
I propose four
Houston
potential
now
cultural
controlling.
approaches
Atlantis
to
begins its
confronting this
penultimate
challenge.
journey to shore
These are
up the
four
International Space
frameworks we
Station.
might adopt as we grapple with the influx of cosmic
Atlantis now in the
oddities that
proper alignment
21st
for its
century
8.5-minute
astronomy
ride
is
to orbit.
revealing.
4.5 million
The
pounds
first
of
is
hardware and
reliance on
humans taking aim
established
on the international
institutions. We
outpost.
place our trust in the scientific community, accepting their findings as
30
provisional yet
seconds into the flight.
authoritative, and resisting
Atlantis
the urge
almost
to
2 miles in
scrutinize every
altitude, almost
uncertainty.
6 miles downrange
This
from the
approach
Kennedy
is
Space Center
effective when
already, traveling
institutions
500
operate
miles
with
an hour.
transparency, accountability, and a receptiveness
The 3
to
liquid fuel main
critique.
engines now throttling back
However,
to
it falters when
72% of
trust
rated performance,
erodes,
going into
either
the
due
bucket,
to
reducing the stress on
institutional
the shuttle as it
opacity
breaks through
or
the sound
significant
barrier.
unacknowledged errors. The second is a demand for complete transparency. We insist that scientific data, particularly that generated by publicly funded instruments, be made accessible for independent examination. We establish pathways for citizen science, enabling non-specialists to contribute to verification efforts. We advocate for open-source algorithms in transient event detection, ensuring the logic behind classifications can be thoroughly reviewed. This strategy empowers collective intelligence but risks overwhelming us with information and fostering a proliferation of conflicting interpretations. The third approach is to foster skeptical humility. We acknowledge that some questions may remain unanswered, at least for the foreseeable future, and we resist the societal pressure to prematurely transform ambiguity into certainty. We openly declare without shame, "I do not know." And we create space for this uncertainty, refraining from filling it with conjecture. This is the most challenging path, as humility does not spread rapidly and certainty does not attract widespread attention. Admitting ignorance can feel like a weakness in a culture that celebrates confidence. Yet this is the path most congruent with the scientific method, which is fundamentally a mechanism for managing uncertainty, not eliminating it. The fourth response is to embrace mystery as a cultural value. We reframe the unknown, not as a problem requiring a solution, but as an intrinsic aspect of existence to be appreciated. We discover awe in the unknown, derive meaning from the questions themselves, and cultivate cultural narratives that celebrate exploration without demanding definitive answers. This is the more romantic perspective, and it risks devolving into anti-intellectualism if not tempered with intellectual rigor. However, it offers a psychologically sustainable means of existing within a universe that will perpetually exceed our grasp. None of these proposed responses are inherently flawed, nor is any single one sufficient on its own. The most prudent course of action likely involves a synthesized approach adapting to specific contexts and evolving circumstances. What remains indisputable is that the old paradigm where a select group of experts disseminated authoritative pronouncements to a passive public is no longer viable. The information landscape has democratized access to data while simultaneously fragmenting shared understanding, and we are collectively navigating toward a new epistemology, a novel method of acquiring knowledge that acknowledges the limitations of expertise without succumbing to complete relativism. Practical strategies exist for guiding this transition, and they warrant articulation even if their implementation proves gradual and inconsistent. Mandates for open access to key astronomical datasets would facilitate independent verification and diminish the perception of exclusivity. Integrating citizen science initiatives with professional verification pipelines would leverage distributed intelligence while maintaining rigorous quality control. Developing enhanced media literacy tools specifically designed to evaluate transient astronomical phenomena would assist non-specialists in distinguishing between credible observations and extraneous data. Implementing standardized provenance annotations for AI-generated alerts would provide subsequent users with crucial context regarding confidence levels and verification status. Establishing collaborative frameworks where amateur and professional astronomers share data in real time would accelerate discoveries while distributing the responsibility for knowledge acquisition. The ramifications of mishandling this transition are not theoretical. Public apprehension can escalate when individuals feel deceived or believe authorities are withholding critical information. Exploitation thrives when ambiguity is deliberately manipulated by those who profit from fear or credulity. Cynicism can become entrenched when every assertion and counter-assertion is indistinguishable from propaganda, leading individuals to retreat into echo chambers where they exclusively trust voices that affirm their pre-existing beliefs. These are not hypothetical risks, they are observable dynamics in how communities respond to various situations, from public health crises to climate science. The stakes are amplified when the subject matter involves the cosmos, which carries a metaphysical significance absent in more mundane topics. Conversely, the advantages of
32 seconds
mature
into the
public
flight.
engagement with these issues
The 3 liquid
are
fuel main
substantial.
engines soon will throttle back to
Scientifically
72% of
informed
rated
populace
performance down in the
capable of
bucket,
grappling
reducing
with
the stress on the
uncertainty
shuttle
is
as it goes
less
transonic.
susceptible to manipulation. A culture that values evidence-based reasoning without demanding unattainable certainty is better equipped to navigate technological advancements and existential threats. A society that views the cosmos as a shared heritage rather than a battleground for competing narratives is more likely to make judicious collective decisions regarding its exploration and how we respond to genuinely extraordinary discoveries. Envision the pre-dawn sky on December 15, 2025. The Day 3 Atlas reaches its perihelion and commences its gradual departure into the void. The comet's luminous tail will stretch across the heavens, a faint but discernible presence for those aware of its location.
10, 9,
3 individuals
8,
stand
7,
in disparate locations
6,
observing the
5,
same celestial event from distinct
3,
perspectives.
2,
The scientist perceives a data
0,
point, the culmination
and
of months
liftoff
diligent
of Space Shuttle
observation, a
Atlantis
crucial element
on a mission
that
to
either
build,
conforms to or
resupply,
challenges
and to do
existing
research
models, a
on the
catalyst for
International
further
Space Station.
inquiry. The cleric
Houston now
interprets it as
controlling.
a
Atlantis
divine
begins its
sign,
penultimate
a
journey to shore up
reminder
the
of
International Space
transcendent,
Station.
an invitation to profound humility.
Atlantis now in the
In the
proper
face of
alignment for its
creation's
8.5 minute line to
immensity,
orbit,
the
4.5
child
million pounds
witnesses
of
a
hardware
streak of
and
light
humans
and
taking aim on the
experiences
international outpost.
unadulterated wonder, devoid of the need for a label, boundless curiosity
30
without the
seconds into the
imperative
flight.
for a definitive
Atlantis almost 2
explanation.
miles in altitude,
Each
almost 6
viewpoint
miles
possesses
downrange
its
from the Kennedy
validity.
Space Center already,
Each is
traveling
incomplete.
500 miles an
The
hour.
phenomenon itself, the comet tracing its arc through
The
space,
3 liquid
remains
fuel main
indifferent
engines
to
now
all
throttling back to
interpretations,
72% of
governed
rated
solely
performance,
by
going
the
into the
immutable
bucket, reducing
laws
the
of
stress on the
physics and
shuttle
the
as it
slow
breaks through the sound
dissipation of
barrier.
its icy core. When celestial lights reappear, as they inevitably will, whether as comets, meteors, or phenomena yet unimagined, the onus of interpretation will fall upon us, not upon the lights themselves, nor the algorithms that detect them, nor the institutions that study them, but upon us, you, me, and everyone else striving to comprehend a universe that owes us no explanations. Our objective is not to eradicate uncertainty. Our aim is to cultivate a society capable of coexisting with it, finding fulfillment in the investigative process rather than solely in the acquisition of answers, and recognizing that the most perilous illusion is not the one projected onto the night sky, but the conviction that we have deciphered mysteries that remain inherently and beautifully unresolved.